Look closely at a snowflake, its delicate, branching arms, its flawless geometric precision. It's one of nature's most perfect examples of symmetry, a work of art frozen in time. But what if I told you that this beauty is only skin deep, that at the most fundamental level, this symmetry is an illusion, a temporary state hiding a deeper, more dynamic truth? The universe, it turns out, doesn't truly love perfect balance. In fact, it thrives on breaking it. The physicist Philip Anderson once wrote, "More is different." And in those 3 words, he captured one of the most profound ideas in all of science, that symmetry breaking is the hidden engine of reality. It's the reason our universe isn't a silent, static, featureless void. Why instead, it's vibrant, evolving, and filled with galaxies, planets, and life. There's a cosmic tension between the elegance of balance and the necessity of imperfection, and that tension is what drives everything we see, feel, and are. So today, we're going on a journey from the first moments after the Big Bang to the inner workings of your own mind. We'll explore how something as beautiful as symmetry could actually break the world we know into being. How did a perfectly uniform fireball give rise to the rich diversity of the cosmos? How did imbalance create atoms, stars, and eventually us? And what does it mean that our very consciousness may be a product of broken symmetry? This is the story of how perfection is not the goal of the universe, becoming is. So settle in. We're about to unravel one of nature's deepest and most beautiful secrets. This deep human fascination with symmetry isn't just an aesthetic preference. It feels like a glimpse into a fundamental order of the universe. We see this reverence for balance carved into the very stones of the Parthenon, its columns and pediments arranged to please the eye with perfect proportion. We find it in the intricate, repeating patterns of Islamic mosaics, designed to reflect the infinite and the divine. We even see it in the natural world, in the radial symmetry of a blooming flower or the spiraling arms of a distant galaxy. There's a profound sense of rightness to it, a feeling that symmetry represents an ideal state of harmony and cosmic equilibrium. But what is symmetry, really, when we strip away the poetry and look at it through the lens of physics? At its core, it's a concept called invariance under transformation. That's a fancy way of saying that the laws of physics don't change, no matter how you look at things. If you rotate an experiment in empty space, the outcome remains the same. If you move it to a different location, the underlying principles are identical. This invariance is what gives us conservation laws, like the conservation of energy or momentum. It's the reason the universe is predictable and lawful instead of chaotic. This kind of perfect symmetry paints a picture of a reality in a state of ultimate balance, a serene and eternal stillness. And for a fleeting moment at the very beginning of everything, that's exactly what we had. Picture the universe an instant after the Big Bang, a searingly hot, unimaginably dense, but perfectly uniform soup of energy. There were no stars, no planets, not even atoms. Every point in space was identical to every other point. Every direction was the same. It was the ultimate expression of cosmic symmetry, a featureless, symmetric egg of pure potential. Yet, this pristine state of perfection was inherently unstable. It held within it the seeds of its own transformation. That perfectly round, featureless universe was like a pencil balanced perfectly on its tip, theoretically possible. But in practice, the slightest perturbation will cause it to fall, choosing a specific direction. And that's the great cosmic puzzle. Why is the universe we observe today so rich, so complex, and so beautifully asymmetric? Why did that perfect symmetry break? But if these symmetries are so fundamental, so deeply woven into the fabric of reality, why isn't our universe a perfectly balanced, static, and frankly, boring place? The answer lies in the most beautiful and powerful loophole in all of physics. These symmetries can be broken. They aren't rigid, ironclad rules, but more like a set of perfect, pristine possibilities. The universe, in its journey from that initial fireball, didn't abandon these laws, it used them. It found that within this elegant framework of symmetry, there are states of lower energy, states of greater complexity that the system can fall into. This is the concept of spontaneous symmetry breaking. Think of it like a marble resting at the very top of a perfectly symmetrical Mexican hat. The setup is symmetric, every direction is equal. But the marble is unstable. The slightest nudge will send it rolling down into the trough, picking one specific, random direction. The symmetry of the system is still there in the laws that describe the hat, but the marble's new state has broken that symmetry. It has chosen a particular path, and in doing so, it has acquired new properties. It's now in motion. It has a specific location. This is exactly the kind of process that sets the stage for all the diversity we see in the cosmos today. The framework of physics is symmetric, but the universe we inhabit is a masterpiece of chosen imperfections, a story written in the language of broken symmetry. So the universe began in a state of perfect, featureless symmetry, a hot and dense soup where every direction was the same and every force was one. For a fleeting moment, all the fundamental forces we know today were unified into a single, supreme force. But this pristine state was not destined to last. As the newborn universe expanded at a furious rate, it also began to cool. And with that cooling came the first great crack in the cosmic egg, an event known as Electroweak symmetry breaking. This was the moment when a single, unified force split in two, giving birth to the electromagnetic force and the weak nuclear force as we know them. Before this pivotal transition, these forces were indistinguishable, described by a beautiful, symmetric set of equations. Particles like the photon, which carries light, and the W and Z bosons, which mediate radioactive decay, were all massless and interchangeable. But as the temperature plummeted, the universe underwent a dramatic phase change, much like steam condensing into water or water freezing into ice. This shift was triggered by a field that permeates all of reality, the Higgs field. In the searing heat of the early universe, the Higgs field had a value of 0 everywhere, maintaining the perfect symmetry. But as things cooled, this became an unstable state, like that pencil balanced perfectly on its tip. The symmetric state was possible, but any tiny fluctuation would cause it to fall, and the Higgs field to settle into a new, non-zero value everywhere. This is the essence of spontaneous symmetry breaking. The laws of physics themselves still possess the symmetry, but the universe we live in does not. The Higgs field chose a value, and in doing so, it broke the symmetry. The consequences of this breaking were nothing short of cosmic. Particles that once zipped around at the speed of light, weightless and free, suddenly began to interact with this now active Higgs field. Think of it like a celebrity trying to move through a crowded room. The crowd represents the Higgs field, an unknown person. A photon slips through easily, remaining massless. But other particles, like electrons and quarks, are like famous celebrities. The crowd gravitates towards them, they get bogged down, and this interaction is what we experience as mass. The W and Z bosons gained a tremendous amount of mass, which is why the weak force has such an incredibly short range, while the photon remained massless, allowing light to travel across the universe. Without this specific, historical breaking of symmetry, the fundamental building blocks of matter would have no mass. Electrons would be unable to bind to atomic nuclei, atoms could never form, and the complex chemistry that leads to stars, planets, and life would be impossible. The universe would be a forever sea of massless particles flashing through an empty darkness, never cohering into anything substantial. This first crack was not a flaw or a mistake. It was the necessary creative act that allowed something to emerge from nothingness, structure to crystallize from uniformity. It set the stage for everything that was to come. So what exactly is this Higgs field that orchestrated such a profound transformation? Imagine an invisible, endless ocean that fills every single cubic centimeter of the universe, from the vast emptiness between galaxies to the space inside the very atoms that make up your body. This isn't a metaphorical concept, it's a real quantum field, a fundamental part of the fabric of reality, much like the electromagnetic field. We call this the Higgs field. In its natural, relaxed state, this field has a non-zero value everywhere. It's this ever-present background hum that particles must interact with as they move through the cosmos. And it's this interaction that we experience as mass. The analogy of a crowd in a room is a helpful one. Picture a bustling cocktail party where a famous celebrity enters. The guests immediately swarm around the star, shaking hands, asking for autographs, slowing their progress to a crawl as they make their way across the room. That celebrity has a very high level of interaction with the crowd, and as a result, they move slowly and with great inertia. They've effectively gained a lot of mass. Now imagine a less famous person, or perhaps a photojournalist, enters the same room. A few people might nod or say hello, but they can move through the crowd with relative ease. Their interaction is weaker, so they have less mass, and then there's the completely unknown person who slips through the party entirely unnoticed, moving at full speed from one side to the other without any resistance whatsoever. This particle, like the photon, has no interaction with the Higgs field and remains utterly massless, forever traveling at the speed of light. This elegant mechanism explains why fundamental particles have such wildly different masses. The top quark, for instance, interacts with the Higgs field very strongly, making it incredibly heavy. The electron has a much weaker interaction, giving it a tiny mass. And the photon doesn't interact at all, remaining without mass. But for decades, this was just a brilliant theoretical framework, a beautiful idea waiting for its confirmation. That confirmation arrived in 2012, when the monumental experiments at the Large Hadron Collider at CERN announced the discovery of the Higgs boson. The Higgs boson itself is not the field, it's a crucial piece of evidence for it. Think of the field as the water in the ocean, and the boson is a ripple or a splash on its surface. By creating these ripples in the Higgs field through incredibly high energy particle collisions, scientists were able to prove, beyond a shadow of a doubt, that the field itself is real. This discovery was a landmark moment in human history, closing a chapter on a 50-year search and solidifying our understanding of how the universe works at its most fundamental level. It confirmed that mass itself is not an innate property handed down from on high, but rather an emergent property, a gift from the universe's broken symmetry. This is the profound creative power of imperfection. The ideal, symmetric state was one where all particles were massless and free, but it was a sterile and barren reality. It was the breaking of that symmetry, the activation of the Higgs field, that granted particles the property of mass, allowing them to clump together, to form atoms, to build up everything from the smallest dust grain to the largest star. The mass that makes up your body, the very substance you are composed of, is a direct result of this ancient cosmic event. Without this fundamental breaking, without this departure from perfect balance, the universe would have no substance, no structure, and no story to tell. But the creative power of symmetry breaking wasn't finished yet. Having gifted particles with mass, the universe now faced another monumental challenge, its own overwhelming uniformity. Even with matter beginning to form, the cosmos was still a featureless, smooth expanse, a sea of near-perfect homogeneity that should have remained that way forever. Gravity, the force that pulls matter together, would have acted equally in all directions, leaving no reason for particles to clump into the magnificent structures we see today. So how did we get from that smooth beginning to a universe filled with galaxies, clusters, and vast cosmic webs? The answer lies in another spectacular episode of symmetry breaking, one that occurred on a truly grand scale, known as cosmic inflation. Picture the universe in its first fleeting fraction of a second. For reasons we are still unraveling, a peculiar type of energy field, known as an inflaton field, came to dominate the cosmos. This field found itself in a state of false vacuum, a high-energy, metastable state, like a ball perched high on a plateau. This state possessed a tremendous negative pressure, and it had a bizarre, counterintuitive effect on spacetime itself. It caused it to expand. Not just expand, but to inflate at an exponential, staggering rate. In less than a billionth of a billionth of a billionth of a second, a subatomic-sized speck of universe was blown up to something larger than our entire observable cosmos today. This period of inflation was a state of incredible symmetry. The inflaton field had the same value across this rapidly expanding volume, making the universe more uniform and smooth than anyone could have previously imagined. But just like the Higgs field before it, this symmetric state was unstable. The inflaton field was slowly rolling down its energy hill, and when it finally reached the bottom, its true, stable vacuum state, the symmetry broke. This event, the end of inflation, was like the universe-wide version of that marble finally rolling into the trough of the Mexican hat. The energy contained within that inflaton field was released in a tremendous burst, reheating the universe and flooding it with the hot plasma of particles that would eventually form everything we know. But here's the most beautiful part. During this incredibly rapid expansion, the universe was not perfectly quiet. At the quantum level, there is always a faint jitter, a fundamental uncertainty often called quantum fluctuation. On these microscopic scales, particles and energy flicker in and out of existence. In the normal course of events, these fluctuations are tiny and short-lived. But during inflation, something miraculous happened. Space itself was expanding faster than the speed of light. This meant that these microscopic quantum fluctuations, these tiny imperfections in the inflaton field, didn't have a chance to smooth themselves out. Instead, they were instantly stretched, frozen, and imprinted directly onto the fabric of the cosmos. A minuscule fluctuation that was once smaller than a proton was suddenly inflated to a scale of millions of light-years. What was a microscopic blip became a macroscopic hill, a region with a tiny bit more energy and matter than its surroundings, all because of a random quantum jitter that got caught in the cosmic wind. When inflation ended, these frozen fluctuations became the seeds for all future structure. They were the slight over-densities, the gravitational anchors, that gave the universe something to build on. In the ensuing billions of years, gravity would patiently pull matter toward these subtle bumps in the cosmic density. More matter gathered, gravitational pull increased, and over eons, these seeds grew into the first stars, the first galaxies, the great clusters, and the vast, filamentary cosmic web that defines the large-scale structure of our universe today. We can still see the echo of these primordial imperfections in the cosmic microwave background radiation, a baby picture of the universe. This faint glow, which fills the entire sky, is not perfectly smooth. It contains tiny variations in temperature, mere millionths of a degree, that map directly onto those initial density fluctuations. Those tiny temperature differences are the fossilized imprint of quantum noise stretched across the heavens by inflation. Without this grand-scale symmetry breaking, without the inflattened field rolling down its hill and ending its perfectly symmetric expansion, the universe would have remained eternally smooth, homogeneous, and utterly barren. There would be no stars to ignite, no planets to form, no structures of any kind. We owe the very existence of galaxies, and by extension ourselves, to this monumental event. It is the ultimate demonstration that the smallest of breaks in symmetry, operating at the quantum scale, can be amplified by the laws of physics to shape the entire cosmos, proving that our universe is truly built upon a foundation of beautiful imperfection. So, with the stage set by inflation, the universe was left with a profound gift, a field of subtle imperfections, a nearly, but not perfectly, smooth distribution of matter and energy, imprinted with those faint quantum fingerprints stretched to cosmic proportions. But these tiny overdensities, these slight gravitational hills in the fabric of space, were just potential. For them to become anything real, they needed a force to act upon them, to amplify them, to turn possibility into reality. That force was gravity. Think of the universe right after inflation as an impossibly vast, perfectly smooth sheet of rubber stretched taut. Now, imagine gently pressing your finger into one tiny point on that sheet. A dimple forms. The rubber is no longer perfectly flat. It has a curvature, a well. Anything small and light resting on that sheet, like a tiny marble, will naturally roll down the slope of that dimple and gather at the bottom. Gravity works in much the same way. A region of space with just a little bit more matter than its surroundings creates a slightly stronger gravitational pull, a dimple in spacetime itself. Nearby matter feels this pull and begins to drift slowly toward it. As more matter gathers, the gravitational well deepens, which pulls in even more matter from a wider area, which deepens the well further. It's a powerful, self-reinforcing feedback loop. Over millions and then billions of years, what began as a microscopic quantum fluctuation, a region of space that was only a fraction of a percent denser than average, steadily snowballed. Vast clouds of primordial hydrogen and helium gas were drawn into these growing gravitational pits. The gas condensed, compressed, and eventually ignited under its own immense pressure, giving birth to the very first stars. These stars then grouped together by the millions and billions, forming the first proto-galaxies, which themselves collided and merged to build the majestic spiral and elliptical galaxies we see today. But there's a catch to this story, a mystery that puzzled astronomers for decades. When we calculate the gravitational pull needed to form galaxies as quickly as they did, and to hold them together as they spin, the math simply doesn't add up using the visible matter alone. The stars and gas we can see just don't provide enough gravity. There had to be something else, something invisible, providing the extra gravitational scaffolding. This is where dark matter enters the narrative. We believe dark matter is a type of particle that doesn't interact with light or electromagnetic forces at all. It simply passes through normal matter like a ghost. But it does have mass, and therefore it exerts a powerful gravitational influence. Because dark matter doesn't interact with light, it couldn't clump together in the same way normal matter did. It couldn't radiate away energy and collapse into dense disks. Instead, it formed vast, diffuse, spherical halos around those initial density fluctuations. These halos acted as gravitational anchors, providing a deep, stable potential well long before the visible gas even began to fall in. The normal, baryonic matter, the stuff that makes up stars, planets, and us, simply flowed into the pre-existing gravitational frameworks sculpted by the dark matter. The breaking of the universe's spatial homogeneity, therefore, was a duet between the visible and the invisible. The initial seeds were planted by quantum fluctuations during inflation. The dark matter provided the foundational architecture, the massive skeleton upon which the visible universe could be built, and gravity was the conductor, orchestrating the entire collapse over cosmic time. Without this intricate collaboration, the universe would have remained just that, a uniform void. The slight asymmetries would never have been amplified. There would be no grand spiral galaxies, no stellar nurseries, no swirling accretion disks giving birth to planets. The cosmos would be static, homogeneous, and ultimately lifeless. The breaking of this perfect symmetry, the introduction of these gravitational wrinkles, was the essential next step in a creative chain reaction that transformed a smooth, featureless fireball into the rich, structured, and dynamic universe we are privileged to call home. And so, with the cosmic architecture in place, with vast clouds of gas and dark matter halos providing the gravitational nurseries, the universe was finally ready for its next great act of creation, the birth of the first stars. This wasn't just about lighting up the darkness, it was about fundamentally transforming the very ingredients of reality through a process of nuclear symmetry breaking. For billions of years, these immense clouds of primordial gas, composed almost entirely of hydrogen and helium, drifted through the cosmic voids. They were cold, dark, and quiet. But within them, gravity was tirelessly at work, patiently pulling atoms closer and closer together. As these giant molecular clouds contracted, their cores grew denser and hotter. For a long time, the inward crush of gravity was balanced by the outward pressure of the gas. But eventually, in the deepest, densest pockets of these clouds, a critical threshold was crossed. The temperature in the core soared to unimaginable levels, millions of degrees. At this extreme heat and pressure, the hydrogen atoms, which normally repel each other due to the positive charge of their protons, were forced into intimate, violent collisions. Their speed overcame the electromagnetic force that kept them apart, and they smashed into each other with enough energy to overcome what's known as the Coulomb barrier. This is the first great nuclear symmetry break. In a state of perfect balance, these two positively charged protons would forever repel one another, never interacting. But the immense local imbalance of energy and pressure in the stellar core breaks that standoff. It allows the even stronger, but much shorter range, strong nuclear force to take over. This force is the ultimate cosmic glue, and it can bind protons together despite their electromagnetic rebellion. In a dazzling sequence of steps, 4 hydrogen nuclei are fused together to create one nucleus of helium. But here's the astonishing part. The mass of that single helium nucleus is ever so slightly less than the combined mass of the 4 hydrogen nuclei that created it. Where did that tiny bit of mass go? It was transformed directly into pure energy, in accordance with Einstein's most famous equation, E equals mc². This is the miracle of nuclear fusion, the engine that powers every star in the sky. That released energy radiates outward from the core, creating an immense pressure that pushes back against the relentless crush of gravity. A stable, brilliant, and long-lived star is born. This is a new equilibrium, but it's a dynamic and temporary one, forged from a broken symmetry. Without this process, the universe would be a very dull and simple place. Hydrogen would forever remain hydrogen. The periodic table would be a very short list, but the breaking of nuclear symmetry inside stars changes everything. As a star ages and exhausts the hydrogen fuel in its core, the balance shifts again. Gravity begins to win, crushing the core further and heating it to even more extreme temperatures, hot enough to begin fusing helium itself. In the heart of massive stars, this process becomes a cosmic forge, creating successively heavier elements. Helium fuses into carbon, carbon into oxygen, neon, magnesium, and on up the periodic table all the way to iron. Each step in this chain requires breaking a new nuclear symmetry, overcoming new repulsive barriers to build ever more complex atomic nuclei, but the process stops at iron. Fusing iron doesn't release energy, it consumes it. With its energy-producing days over, the star's core abruptly collapses under its own immense weight. In a cataclysmic event known as a supernova, the outer layers of the star are blasted outward in one of the most energetic explosions in the universe. For a brief moment, a single supernova can outshine an entire galaxy. In this unimaginable inferno of energy and neutrons, the final act of cosmic alchemy occurs. Elements heavier than iron like gold, silver, uranium, and iodine are forged in the intense bombardment of the blast and then scattered far and wide across the interstellar medium. This is the ultimate gift of the stars. The life cycle of a star, from its quiet birth in a gas cloud to its violent death in a supernova, is a story of imbalance driving evolution. The gravitational imbalance creates the star, the nuclear imbalance fuels it and builds complexity, and the final catastrophic imbalance scatters the newly forged elements across space. Every atom of oxygen you breathe, every particle of carbon in your cells, every trace of iron in your blood, was once forged in the heart of a long-dead star and then seeded into the cosmos by its spectacular death. We are literally made of stardust, the direct result of nuclear symmetry breaking on a cosmic scale. This process exemplifies the beautiful, paradoxical truth at the heart of reality. It is only through the breaking of perfect symmetry, through the embrace of dynamic imbalance, that the universe can become something more than it was. So the universe was now seeded with the heavy elements forged in stellar hearts, but these precious materials were scattered far and wide, adrift in the vast emptiness between the stars. For planets to form, for worlds like our own to ever exist, this cosmic dust and gas needed to gather to find a new gravitational anchor and begin a new process of construction. This brings us to the next critical stage of cosmic becoming, the formation of planets, a story once again driven not by perfect symmetry, but by fruitful, creative asymmetry. It all begins with the remnants of a dead star. When a massive star goes supernova, or when a smaller star like our own sun sheds its outer layers, it doesn't just blast its enriched contents into the void. The explosion also sends out powerful shock waves that can slam into nearby, relatively quiet clouds of molecular hydrogen. This violent compression can trigger the gravitational collapse of these clouds, causing them to fragment and coalesce into a new generation of stars. As a new star forms at the center of this collapsing cloud, conservation of angular momentum causes the surrounding material to flatten into a spinning, pancake-like structure known as a protoplanetary disk. This disk, made of gas and microscopic dust grains, is the primordial nursery for planets. In its earliest stages, this disk might appear remarkably smooth and symmetric, rotating gracefully around its infant sun. But this symmetry is once again fleeting. Tiny, random variations in the density of the disk are all that's needed to start a chain reaction. A slightly denser clump of dust exerts a slightly stronger gravitational pull, attracting more particles to it. As these planetesimals grow from dust grains to kilometer-sized bodies, their gravitational influence increases, allowing them to sweep up more and more material in their path. This process, called accretion, is fundamentally chaotic and asymmetric. It's a cosmic game of bumper cars on a grand scale, with countless collisions, some gentle mergers, others violent, shattering impact. The outcomes of these collisions are never perfectly balanced. One glancing blow might spin a growing body faster, while a direct hit might strip away its atmosphere. Over millions of years, this chaotic dance of accretion, guided by gravity, results in a handful of stable planets clearing their orbital paths. Our own solar system is a perfect museum of this asymmetric process. Close to the bright, hot young sun, only materials with high melting points, metals and rocky silicates, could remain solid. This led to the formation of the dense, rocky inner planets, Mercury, Venus, Earth, and Mars. Farther out beyond the frost line, volatile compounds like water, ammonia, and methane could also condense into ice, providing much more building material. This allowed the cores of the outer planets to grow massive enough to gravitationally capture the vast reservoirs of hydrogen and helium gas still present in the disk, becoming the gas giants Jupiter and Saturn and the ice giants Uranus and Neptune. This stark division itself is a form of broken symmetry, a clear gradient from dense rock to gaseous giants, a direct result of the temperature and pressure asymmetry radiating from the Sun. But the asymmetries don't stop at planetary classification. Look at the axial tilts of the planets. Uranus is practically rolling on its side compared to the others. Venus rotates backwards. These are likely the scars of colossal, off-center impacts during the late stages of planetary formation, permanent records of the violent and random nature of their birth. And then there's Earth itself. From space, our planet might appear as a beautiful, symmetrical blue marble, but this is an illusion. The distribution of its continents and oceans is strikingly asymmetric. The Pacific Ocean covers nearly one entire hemisphere, while land dominates the other. This is not a random accident. It is the dynamic result of plate tectonics, driven by the asymmetric convection of heat from our planet's interior. This very asymmetry is a cornerstone of our planet's habitability. The contrast between land and sea drives ocean currents and weather patterns, regulating climate and distributing nutrients across the globe. The constant recycling of the crust through tectonics regulates atmospheric carbon dioxide over geologic timescales, preventing a runaway greenhouse effect and maintaining a stable climate, a key ingredient for life. Imagine a hypothetical Earth that was perfectly symmetric, with land and water distributed in perfectly even, alternating bands. Such a world would have far less climatic variation, far less nutrient mixing in the oceans, and likely far less biodiversity. It would be a far more static and arguably a far less interesting planet. The majestic mountain ranges, the deep ocean trenches, the vast deserts, and the lush rainforests, all these features that make Earth so breathtakingly diverse are direct consequences of its inherent asymmetries. A perfectly symmetrical planetary system would be a collection of identical, featureless spheres following perfectly circular orbits. It would be a system of order, but also of sterility. It is the embrace of imperfection, the off-center collisions, the random mergers, the uneven distribution of elements, that creates the stunning diversity of worlds we see in our own solar system and beyond. From the volcanic fury of Io to the methane lakes of Titan, from the iron core of Mercury to the icy shell of Europa, each world is a unique testament to the creative power of broken symmetry, proving that it is only through imbalance that the universe can build worlds capable of harboring wonder. And so we arrive at one of the most intimate and profound examples of symmetry breaking in the entire cosmic story, the very origin of life itself. After eons of stellar furnaces forging heavy elements and violent planetary accretion scattering them across new worlds, the stage was finally set on at least one tiny, watery planet. The ingredients were all there: liquid water, organic molecules, and a steady energy source. but to jump from a primordial soup of chemicals to a living, replicating cell required one more crucial, subtle break from perfection, this time at the deepest molecular level. This is the mystery of biological homochirality. The term chiral comes from the Greek word for hand, and it describes molecules that are non-superimposable mirror images of each other, much like your left and right hands. They have the same atoms, the same bonds, but they are arranged in a way that makes them fundamentally different, unable to be stacked perfectly on top of one another. In the laboratory, when chemists synthesize amino acids, the building blocks of proteins or sugars, they always create a perfect 50-50 racemic mixture. For every left-handed molecule spun into existence, an identical right-handed counterpart is also created. This is the symmetric expected outcome. But when we look at the machinery of life on Earth, we find something astonishingly different, a massive breaking of this symmetry. Every single protein in every living thing on this planet is built exclusively from left-handed amino acids. Conversely, the backbone of DNA and RNA, the sugar-phosphate ladder, is built exclusively from right-handed sugars. This isn't a minor preference, it's a universal and absolute rule for all known life. This molecular handedness or chirality isn't just a curious biological footnote, it is absolutely essential for life's function. Think of it like trying to build a complex machine using both right-handed and left-handed screws and bolts. The components simply wouldn't fit together properly. In the same way, the exquisite specificity of enzymes, the molecular machines that catalyze every reaction in your body, relies entirely on a consistent handedness. An enzyme's active site is a carefully sculpted, three-dimensional pocket that only a substrate with the correct shape can fit into, like a key in a lock. If even a few right-handed amino acids were inserted into an enzyme designed for left-handed ones, the entire structure would warp and the key would no longer fit the lock. The precise double helix structure of DNA itself depends on every sugar molecule having the same right-handed conformation. A mixed-handedness DNA strand would be a tangled, dysfunctional mess, utterly incapable of storing genetic information or replicating itself faithfully. So how did this fundamental asymmetry arise from a presumably symmetric, prebiotic world? This is one of the great open questions in science, and several compelling theories point to external influences that could have acted as a tiny nudge, breaking the symmetry just enough to tip the scales. One fascinating idea involves circularly polarized light. In the vast molecular clouds of space, where complex organic molecules are known to form on the surfaces of dust grains, light from nearby stars can become polarized as it passes through magnetic fields. This twisted light could potentially destroy one chiral form of a molecule slightly more than the other. Meteorites that have fallen to Earth, like the famous Murchison meteorite, have been analyzed and show a slight excess of left-handed amino acids, providing tantalizing evidence that this chiral bias might have been delivered to our planet from space, seeded directly from the cosmos. Another theory points to the crystalline surfaces of certain minerals. Common minerals like quartz and calcite can themselves have chiral surfaces, arrangements of atoms that spiral in either a left-handed or right-handed direction. As prebiotic molecules washed over these surfaces in ancient tidal pools or hydrothermal vents, one form might have been preferentially adsorbed or catalyzed into longer chains, effectively selecting for a particular handedness and amplifying a tiny initial imbalance over time. Once a small bias was established, a process called autocatalysis could have taken over, where molecules of a specific handedness help create more copies of themselves in a runaway, self-reinforcing feedback loop. What began as a minuscule statistical fluctuation, perhaps just a fraction of a % more left-handed amino acids, could have been amplified over millennia into the overwhelming homogeneity we see in biology today. This transition from chemical symmetry to biological asymmetry represents a critical threshold in the story of our universe. It marks the point where the cosmic imperative for imbalance moved from shaping galaxies and stars to orchestrating the intricate dance of biochemistry. The universe didn't just break symmetry to create mass or structure. It broke symmetry to create function, specificity, and ultimately meaning. Life is not a passive passenger in a universe of chance. It is an active expression of the fundamental principle that becoming requires a departure from equilibrium. The very fact that you are built from molecules with a specific handedness is a direct inheritance from this ancient event, a living testament to the fact that our existence hinges on a broken symmetry that occurred billions of years ago, proving that imperfection is not just a feature of the cosmos, but the very essence of life itself. This drive toward asymmetry isn't just a quirk of anatomy. It extends deep into the very behaviors and functions of living things, revealing how natural selection actively dismantles symmetry for the sake of efficiency and survival. Consider something as fundamental as handedness in humans. We are not a species of perfect ambidextrous beings. The vast majority of us have a dominant hand, a foot we prefer to kick with, even a dominant eye. This lateralization, this bias in our limb use, is a form of behavioral symmetry breaking hardwired into our brains. From an evolutionary perspective, this specialization makes perfect sense. There's a significant metabolic cost to developing and maintaining complex neural circuitry. By specializing one side of the brain for fine motor control, like the precise manipulation needed to craft a stone tool or throw a spear, our ancestors conserved precious cognitive resources. The other hemisphere could then be freed up for other crucial tasks, like monitoring the environment for predators or managing social interactions within a group. This neural asymmetry allowed for a parallel processing of information, a multitasking that provided a clear survival advantage. It's far more efficient to have one highly skilled hand than two moderately skilled ones. This principle of functional asymmetry is echoed throughout the animal kingdom. Parrots, for instance, are almost always left-footed or right-footed, using their preferred foot to dexterously manipulate food and objects. This isn't random, it's a refined adaptation for feeding. Even the humble scale-eating cichlid fish of Africa's Great Lakes provides a stunning example. These fish attack other fish from behind, sneaking up to bite scales off their flank. But they have a problem. Their prey scales are arranged in overlapping rows, much like shingles on a roof. To successfully pry a scale loose, the attacker must approach from one specific direction. Astonishingly, individual cichlids are born with their mouths twisted either permanently to the left or to the right, a morphological asymmetry that dictates their entire hunting strategy. This broken symmetry eliminates hesitation. A left-mouthed fish always attacks from the right and vice versa, making it a highly efficient specialist. The tension here is beautiful. A perfectly symmetrical mouth would be a generalist's tool, theoretically allowing attacks from any angle. But evolution, through natural selection, consistently breaks that symmetry, favoring specialized, asymmetrical forms that deliver a superior, if narrower, advantage. This relentless pressure for optimization means that perfect, balanced symmetry is often a starting point, a blank slate upon which the messy, practical demands of real life are written. An embryo may begin its development with beautiful bilateral symmetry, but as it grows, adaptive pressures sculpt it, pushing and pulling its form into something more lopsided, more efficient, and more uniquely suited to its particular niche in the world. This is the brilliant, creative engine of evolution. It doesn't seek perfect balance, it seeks solutions. And in a world of limited resources and fierce competition, The most elegant solutions frequently involve a departure from symmetry, a tilt in one direction that provides a crucial edge. The breathtaking diversity of life on our planet, from the twisted shell of a snail to the asymmetrical face of an owl, stands as a monumental testament to this process. It is a living gallery of imperfections, each one a story of how becoming, in all its glorious and functional variety, requires a decisive break from equilibrium. And this drive toward functional asymmetry finds perhaps its most sophisticated expression not in our limbs or our behavior, but within the very organ that makes us human, the brain itself. For centuries, we've used the concept of left brain and right brain as a kind of popular shorthand for logic versus creativity. But the real story of our brain's lateralization is far more fascinating and complex. It represents a profound neural breaking of symmetry, a division of labor that is the very foundation of our advanced consciousness. On the surface, the two hemispheres of your brain appear to be nearly perfect mirror images. But this structural symmetry is a beautiful deception. Dive beneath the surface into the intricate wiring and functional organization, and you discover a world of stunning asymmetry. This lateralization isn't a bug in our system, it's a masterstroke of evolutionary optimization. The left hemisphere, in most right-handed individuals, has become the dominant center for language processing. It's where we find Broca's area, crucial for speech production, and Wernicke's area, essential for language comprehension. This hemisphere excels at linear, logical processing, at breaking down complex sequences into manageable steps. It's the part of the brain that thrives on detail, order, and analytical thought. The right hemisphere, by contrast, specializes in a different but equally vital set of skills. It is the master of the big picture, of spatial awareness and holistic perception. It is deeply involved in recognizing faces, interpreting emotional tone in a voice, and appreciating music and art. It thinks not in words but in images and patterns, and it is the wellspring of our intuition and creative leaps. This division of cognitive labor is a brilliant efficiency strategy. By dedicating specific neural real estate to specialized tasks, the brain avoids the costly redundancy of having two hemispheres trying to do exactly the same job. It's like having two experts in a workshop instead of two generalists. One is a master cabinetmaker focused on the fine joinery, while the other is an architect who sees the entire design and how all the pieces fit together in the space. This allows for a form of parallel processing, where both hemispheres can work on different aspects of a problem simultaneously, dramatically increasing our cognitive horsepower. The most compelling evidence for this functional asymmetry comes from a radical surgical procedure performed in the mid-20th century on patients with severe, untreatable epilepsy. In a last resort effort to prevent violent seizures from spreading across the entire brain, surgeons would sever the corpus callosum, the thick bundle of over 200 million nerve fibers that serves as the superhighway of communication between the two hemispheres. These split-brain patients recovered and seemed, at first glance, surprisingly normal. But under carefully designed experimental conditions, their reality revealed the profound consequences of this disrupted symmetry. In one famous experiment, a patient would focus on a dot in the center of a screen. The word key would be flashed very briefly to the left of the dot, sending the visual information only to the right hemisphere, which controls the left side of the body and visual field. Then the word ring would be flashed to the right of the dot, sending information to the language-dominant left hemisphere. When asked what word they saw, the patient would confidently say ring, because their left hemisphere, which controls speech, only saw that word. But then came the astonishing part. With their left hand controlled by the right hemisphere that saw the word key, the patient could easily pick out a key from a collection of hidden objects. When asked why their left hand was holding a key, the left hemisphere, which had no knowledge of the word key, would instantly confabulate a logical-sounding reason. "Oh, that's just a key I have from home," it might say, creating a story to make sense of an action it didn't initiate. These experiments revealed a mind-bending truth. Severing the connection between the hemispheres didn't create one incapacitated brain, but rather two conscious, aware minds within a single skull. The verbally articulate left hemisphere and the silent but perceptive right hemisphere were each processing their own reality, their own stream of consciousness, now trapped in isolation from each other. This shows us that our unified sense of self, our singular experience of the world, is a carefully constructed illusion maintained by the constant, lightning-fast dialogue across the corpus callosum. When that symmetry of communication is broken, the underlying asymmetry of our cognitive machinery is laid bare. This neural architecture is a powerful testament to the cosmic principle we've been following. The human brain did not evolve toward perfect bilateral symmetry. It evolved toward an optimized, efficient imbalance. The breaking of symmetry in our neurology is what allows for the breathtaking complexity of human language, the depth of logical reasoning, and the soaring heights of creative innovation. It is this very asymmetry that enables you to appreciate the logical structure of a mathematical equation with your left hemisphere, while simultaneously feeling the emotional resonance of a piece of music with your right. It is the tension and collaboration between these two specialized worlds that gives rise to the rich tapestry of human consciousness and culture, proving once again that the most advanced structures in the universe are built not on a foundation of perfect balance, but on the dynamic and creative power of calculated imperfection. This journey from the quantum to the cosmic, from the biological to the neurological, reveals that the drive toward asymmetry is not merely a physical law but a deeply embedded creative principle. And nowhere do we see this principle embraced more consciously and joyfully than in the vast tapestry of human culture and art. For millennia, artists, architects, and musicians have intuitively understood a profound truth that science is only now fully articulating. While symmetry provides a foundation of order and beauty, it is the deliberate break from that perfection that breathes life, emotion, and soul into a creation. Consider the very symbol of classical symmetry we mentioned earlier, the Parthenon. For centuries, it was held up as the pinnacle of balanced, harmonious design. But meticulous measurements have revealed that the ancient Greek architects were master illusionists. The platform on which the Parthenon sits isn't actually flat. It curves upward slightly in the middle to counter the optical illusion that a perfectly straight base would appear to sag. The columns aren't perfectly vertical. They tilt inward just a fraction of a degree, and they also exhibit a subtle swelling in the middle called intosses, which prevents them from appearing pinched and fragile. Even the spacing between the columns is intentionally irregular. These weren't mistakes or settling over time. They were brilliant, calculated asymmetries designed to make the building appear more perfect, more dynamic, and more alive to the human eye standing below it. The Greeks knew that a mathematically perfect structure would feel cold and lifeless, so they built in these subtle imperfections to engage the viewer on a deeper, almost subconscious level. This same philosophy echoes through the history of painting. The Renaissance masters, for all their focus on proportion and perspective, were experts at using asymmetry to tell a story and guide the viewer's eye. Leonardo da Vinci's The Last Supper is a masterpiece of balanced composition with Christ at the center, but the true drama and emotion come from the asymmetrical chaos that erupts on either side, the groups of apostles reacting in shock, confusion, and horror. their gestures and expressions creating a dynamic tension that pulls us into the narrative moment. A perfectly symmetrical arrangement of figures would have conveyed order, but it would have completely failed to capture the profound human emotion of the scene. Move into the realm of music and the pattern holds. A perfectly symmetrical musical piece, with every phrase answered by an identical response and every rhythm perfectly predictable, would be mind-numbingly boring. It is the break from expectation that creates feeling. In a Bach fugue, the mathematical symmetry of the counterpoint provides the underlying structure, but it's the slight variations, the developments, and the resolutions that stir the soul. In jazz, the entire art form is built on asymmetry, on syncopation, where the accent falls on the offbeat, creating a rhythmic tension that makes you want to move. And improvisation is the ultimate embrace of asymmetric creation. A musician takes a symmetrical chord structure and uses it as a launching pad to explore unique, unpredictable, and deeply personal melodic pathways. This tension and release is the heart of musical emotion. Literature and poetry are no different. While a sonnet has a very strict symmetrical structure of 14 lines and a specific rhyme scheme, the power of a great sonnet comes from how the poet uses that structure to frame a deeply asymmetric, complex, and often conflicting human emotion. The volta, or the turn in the argument between the octet and the sestet, is a deliberate rupture in the logical flow, a moment of asymmetry that delivers the poem's emotional punch. Even in free verse, poets use irregular rhythms, line breaks, and caesures to create a unique cadence that mirrors the natural, asymmetric rhythms of thought and speech. This widespread cultural embrace of imbalance tells us something fundamental about the human spirit. We are drawn to symmetry because it speaks to our longing for order, stability, and ideal forms. It is the language of the eternal and the divine, but we are moved by asymmetry because it is the language of life itself, of growth, change, struggle, and individuality. It is dynamic, unpredictable, and infinitely more interesting. A perfectly symmetrical face might be considered beautiful, but it is the slight quirks and imperfections that make a face memorable and full of character. In our art, as in our universe, perfection is a beautiful starting point, but it is the breaking of that perfection that truly allows for becoming. Our greatest cultural achievements are not monuments to flawless balance, but celebrations of the dynamic, creative, and beautiful tension that exists between balance and imbalance. But if the fundamental laws of physics are so deeply symmetric, why does our experience of the universe feel so decidedly one way? We remember the past, but not the future. A cup shatters on the floor, but the pieces never spontaneously reassemble themselves. We grow older, never younger. This is the mystery of time's arrow, and it points to perhaps the most fundamental asymmetry of all, the breaking of temporal symmetry. The bizarre and beautiful truth is that the microscopic laws of physics, the equations that govern the dance of particles, are almost entirely time-symmetric. If you were to take a video of two electrons colliding and scattering off one another, and then play that video backwards, the reversed motion would also be a perfectly valid solution to the equations of physics. There is no inherent forward or backward built into the laws themselves, and yet the universe as a whole possesses a powerful, undeniable directionality. The reason for this lies in a concept that is both simple and profoundly deep: entropy. Entropy is essentially a measure of disorder, of the number of ways the microscopic components of a system can be arranged while still looking the same from a big picture perspective. And the second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It never decreases. This is the physical basis for the arrow of time. Think of that shattered cup. There is only one way for all the ceramic shards to be arranged to form a perfect, intact cup that's a state of very low entropy. But there are nearly an infinite number of ways for those shards to be scattered across the floor. That's a state of high entropy. The universe, following the second law, naturally evolves from the rare, ordered state to the common, disordered one. The pieces fly apart because that is the overwhelmingly more probable thing to happen. The reassembly, while not impossible according to the underlying physics, is so astronomically improbable that it is never observed. But this just pushes the question back a step. Why was the entropy ever low to begin with? The ultimate source of time's arrow, therefore, is not in the laws themselves, but in the initial condition of our universe. The Big Bang represents a state of incredibly low entropy, a moment of exquisite and inexplicable order. This is the great foundational breaking of temporal symmetry. The universe was wound up, so to speak, at the beginning, and it has been unwinding and increasing in entropy ever since. All the arrows we experience, the psychological arrow of memory, the cosmological arrow of expansion, even the causal arrow, emerge from this single primordial fact. Our ability to remember the past but not the future is a direct consequence of this entropic gradient. Memories are formed by creating order in our brains, a process that increases entropy elsewhere by dissipating heat, for example. We can only have records of the past because the past is the direction of lower entropy. A fascinating thought experiment that highlights the deep connection between information and this temporal asymmetry is Maxwell's demon. Imagine a tiny, intelligent demon controlling a small door between two chambers of gas. The demon can see individual molecules. It only opens the door to let fast-moving molecules pass into one chamber and slow-moving molecules into the other. Over time, one chamber becomes hot and the other cold, seemingly decreasing the overall entropy of the system and violating the second law. For over a century, this paradox puzzled physicists. The resolution came with the realization that the demon itself is part of the system. To know which molecules are fast and slow, the demon must acquire information about them. It must measure and remember their speeds. This act of acquiring information and then using it to sort the molecules is a physical process that generates entropy. When the demon eventually erases its short-term memory to make room for new measurements, that erasure process inevitably dissipates energy and increases entropy by an amount that always outweighs any local decrease. The demon cannot beat the second law because information is physical, and its manipulation is tied irrevocably to the flow of entropy and thus to the arrow of time. This profound link shows that our experience of time, of cause preceding effect, of memory defining our identity, of the irreversible flow from past to future, is not an illusion. It is a fundamental feature of the cosmos, embedded into the fabric of reality by that one singular, low-entropy state at the beginning of everything. The breaking of temporal symmetry is what allows for history, for narrative, for growth and decay. It is the reason the universe has a story to tell, rather than just being a static, eternal tableau. It is the ultimate embedding of becoming into the very heart of existence. But this journey into the nature of reality takes us to an even more perplexing frontier, a realm where the very act of looking at something seems to force it to make a choice. We've seen how symmetry breaks on cosmic and biological scales, but what about at the quantum level, where possibility itself exists in a state of perfect, undecided balance? This brings us to one of the most enduring mysteries in all of science, the quantum measurement problem, a process that shatters a universe of maybes into a world of definitive is. At the heart of quantum mechanics lies the wave function, a mathematical description that encapsulates everything that can possibly be known about a particle, its position, its momentum, its spin. Before any measurement is made, this wave function exists in a state of pure potentiality, a superposition of all possible states. An electron is not here or there. It is, in a very real sense, both here and there, its probability cloud smeared across space. This is a state of perfect probabilistic symmetry. All outcomes are equally valid, held in a delicate, balanced coexistence. The equations that describe this state are beautifully deterministic and symmetric in time. But then, something profound happens. The moment we attempt to measure the system to pin down the electron's location or determine its spin, this symphony of possibilities collapses. The symmetric wave function, which described a smear of probabilities, suddenly and irrevocably snaps into a single, definite outcome. The electron is found here, not there. Its spin is up, not down. The measurement has broken the symmetry of possibilities, actualizing one concrete reality from a fog of infinite potential. Why does this happen? What constitutes a measurement? The equations of quantum mechanics don't provide an answer. They simply state that upon observation, the wave function collapses. This is the central enigma, the most famous thought experiment designed to highlight the sheer strangeness of this process is Schrödinger's cat. Imagine a cat sealed in a box with a diabolical device, a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the radioactive atom decays, the Geiger counter triggers, the hammer smashes the vial, and the cat dies. According to quantum rules, the radioactive atom is in a superposition. It has both decayed and not decayed until it is observed. Therefore, until someone opens the box and looks inside, the entire system, including the poor cat, must be in a superposition of being both alive and dead. It's an absurdity designed to show the conflict between the quantum world's fuzzy probabilities and our macroscopic world's definite realities. We never find a cat that is half alive and half dead. We find one or the other. The act of observation, the measurement, seems to be the trigger that forces the universe to choose. This collapse is the ultimate quantum symmetry break. It is the moment the universe transitions from a state of balanced potential to an asymmetric, concrete fact. But if measurement causes the collapse, what exactly is a measurement? Is it the interaction of a subatomic particle with a macroscopic Geiger counter? Is it the conscious awareness of a human observer? This question plunges us into deep philosophical territory, intertwining physics with the mystery of consciousness itself. Some interpretations suggest that there is no collapse at all, that every possible outcome of a quantum event actually occurs, but in a vast, branching multiverse of parallel realities. In this many-worlds interpretation, the symmetry isn't broken, it's preserved. The wave function never collapses. Instead, the observer becomes entangled with the system, and the single universe splits. In one branch, you open the box and find a living cat. In another, equally real branch, a version of you finds a dead one. The asymmetry we perceive is just an illusion of our limited perspective within one branch. Other interpretations propose that collapse is a real physical process, perhaps driven by continuous spontaneous localization or by the gravitational influence of the measuring device. But the most provocative idea remains the link to consciousness, that the conscious mind itself plays a role in actualizing reality from possibility. This doesn't mean we create reality with our thoughts, but rather that a definite reality may only come into being through a conscious interaction with it. This process, whether it's a physical collapse or a branching into parallel worlds, is fundamental to the fabric of our experience. It is the mechanism by which the universe resolves its inherent uncertainties, making the transition from the quantum realm of balanced potential to the classical world of definite form and history. Every moment, everywhere, trillions upon trillions of these tiny symmetry breaks are happening, crystallizing probability into actuality, weaving the continuous tapestry of becoming from the raw material of quantum possibility. But for all the creative power of these broken symmetries, we are left with one of the most profound and existential questions of all. Why does anything exist? Why is there a universe filled with galaxies, stars, planets, and us, instead of just a featureless, eternal sea of light? To answer that, we have to go back to the very beginning, to a puzzle so deep it threatens the very notion of our existence. According to our best theories, the Big Bang should have created a perfectly symmetric universe in one more crucial way. It should have produced equal amounts of matter and antimatter. For every quark spun into existence, an antiquark should have been its perfect mirror. For every electron, a positron, and this presents a cosmic catastrophe. We know that when a particle meets its antiparticle, they annihilate each other in a brilliant flash of pure energy, returning to the radiation from which they came. If the universe had begun in a state of perfect matter-antimatter symmetry, all of those particles would have found their antiparticle partners within the first second of existence. Every proton would have met an antiproton, every electron a positron. The entire material content of the cosmos would have been completely erased, leaving behind a vast, expanding, and utterly empty universe containing nothing but a dim, cooling bath of radiation. There would be no atoms, no chemistry, no stars, and certainly no one around to wonder why. Yet here we are, our bodies, our planet, our galaxy, everything we can see is made overwhelmingly of matter. So what happened to all the antimatter? This is one of the greatest mysteries in physics, and the only plausible answer is that the symmetry between matter and antimatter was not perfect. There must have been a tiny, almost imperceptible crack in that mirror, a fundamental bias written into the laws of physics that favored matter over antimatter by just 1 part in a billion. This tiny excess of matter is all that survived the Great Annihilation. Everything we see in the universe today is the leftover ash from that near-total self-destruction. The search for the mechanism behind this bias led physicists to a concept known as CP violation. CP stands for charge and parity. Charge conjugation symmetry means that the laws of physics should be the same if you swap every particle with its antiparticle. Parity symmetry means the laws should be the same if you view the universe in a mirror, flipping left and right. For a long time, physicists believed the combination of these two symmetries, CP symmetry, was unbreakable, that the universe would behave identically if you simultaneously swapped matter for antimatter and viewed it in a mirror. But in 1964, physicists James Cronin and Val Fitch made a shocking discovery. They were studying the decay of strange particles called neutral kaons and their antiparticles. If CP symmetry held perfectly, these two particles should have been perfect mirror images, decaying in exactly the same way and at exactly the same rate. But Cronin and Fitch found a slight but definite difference. The kaon and the antikaon did not decay symmetrically. This was a monumental discovery, proving that the laws of physics themselves contain a tiny built-in preference, a subtle thumb on the scale for matter over antimatter. It was a violation of a sacred symmetry, and it earned them the Nobel Prize. We now know that this CP violation is incorporated into the standard model of particle physics. But there's a problem. The amount of CP violation we have found in laboratories is far too small to account for the overwhelming dominance of matter in our universe. The effect we can measure would only produce a matter-antimatter asymmetry 1/10 to 1,000th the size of what was needed to leave behind the universe we see. This means there must be other, much stronger sources of CP violation out there, waiting to be discovered in new particles or new physics beyond our current understanding. This search is a primary goal of massive particle accelerators like the Large Hadron Collider and future experiments designed to study the behavior of other particles, like neutrinos and their antiparticles, with exquisite precision. The implications of this are staggering to contemplate. Our entire reality, the very fact that we exist, hinges on a minuscule 1 in a billion imperfection in the laws of the universe. A perfect, symmetric universe would have been a void. It was this specific broken symmetry that allowed a tiny residue of matter to survive the initial cataclysm, providing the raw material for every galaxy, star, and planet that would later form. We are not just made of stardust, we are made of the 1 billionth that survived, the ultimate testament to the idea that existence itself is a gift of imperfection. But if the universe's laws favor matter so subtly, they warp the very fabric of reality itself under extreme conditions, creating cosmic objects that are the ultimate expression of broken symmetry, black holes. These are not just regions of strong gravity, they are places where the geometry of spacetime is so severely distorted that it shatters the fundamental symmetries we take for granted. Imagine the concept of time translation symmetry, which tells us that the laws of physics don't change from moment to moment. An experiment performed today should yield the same result as an identical experiment performed tomorrow. This symmetry is what gives us the conservation of energy, but a black hole challenges this principle in a profound way for any outside observer. The boundary of a black hole, its event horizon, acts as a point of no return. Once anything, matter, light, even information itself crosses this threshold, it can never come back to communicate with the outside universe. For someone watching from a safe distance, something truly bizarre appears to happen. As an object falls toward the event horizon, its image seems to slow down, becoming redder and dimmer due to the immense gravitational time dilation. From the outside perspective, the object never actually crosses the horizon. It appears to hover, frozen in time, forever approaching but never reaching that final boundary. This means that for the external universe, time translation symmetry is effectively broken at the event horizon. The state of the universe is not the same from one moment to the next in relation to the black hole. It forever contains this object frozen in its final moments, a permanent scar on the timeline. The black hole has memory. It retains the information about everything that ever fell into it, etched onto its surface in a state of perpetual almost. This challenges our very notion of how time and causality should behave. But the story of symmetry breaking around black holes becomes even more fascinating when we introduce quantum mechanics. According to classical physics, a black hole is a perfect one-way street. It can only grow, consuming mass and energy, becoming ever larger and more permanent. It possesses a terrifying symmetry. It has no hair, meaning that to an outside observer, a black hole can be completely described by just 3 properties: its mass, its electric charge, and its spin. All other details about the material that formed it or fell into it are irretrievably lost, hidden behind the veil of the event horizon. This perfect simplicity is a kind of symmetry in its own right. But quantum physics, as it so often does, disrupts this serene and ominous picture. In the 1970s, Stephen Hawking made a revolutionary calculation. He realized that the vacuum of space isn't truly empty. It's a seething foam of virtual particle-antiparticle pairs constantly flickering in and out of existence, borrowing energy from the universe for a fleeting moment before annihilating and paying it back. This is a symmetric process, with pairs being created and destroyed in perfect balance. but Hawking asked what would happen if this quantum fluctuation occurs right at the very edge of a black hole's event horizon. In this extreme environment, the gravitational tidal forces are immense. It's possible for one particle from the virtual pair to fall into the black hole while the other escapes into space. The particle that escapes carries away energy, and to conserve energy, the particle that falls in must have negative energy. This effectively reduces the mass of the black hole. From the perspective of an astronomer far away, it appears as if the black hole is emitting a faint glow of particles, now known as Hawking radiation. This process is a spectacular breaking of quantum symmetry. The perfect balance of the vacuum is disrupted by the black hole's gravity, leading to a net flow of energy outwards. This means black holes are not eternal. They slowly evaporate, losing mass over astronomical timescales until they potentially vanish entirely. This introduces a new asymmetry. Black holes have a lifetime. They are born, they live, and they die. But Hawking's discovery led to one of the most profound puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information is never truly lost. The state of a system at one time should always, in principle, be calculable from its state at a later time. This is a fundamental symmetry of quantum law. But if a black hole evaporates completely through Hawking radiation, what happens to all the information about the stars, planets, and particles that ever fell into it? Hawking radiation itself is thermal. It's random and featureless, depending only on the black hole's mass, temperature, and spin. It appears to carry no information about what was consumed. If the black hole vanishes, that information seems to be erased from the universe forever, violating a core principle of quantum theory. This paradox represents a direct clash between the smooth, continuous geometry of general relativity and the discrete, information-preserving rules of quantum mechanics. Resolving it is thought to be a key step toward a theory of quantum gravity. Some theories suggest the information is somehow encoded on the event horizon itself and is slowly leaked out in the Hawking radiation, though in a horribly scrambled, complex form. Others propose more radical ideas, like remnants or connections to other universes. The very existence of this paradox shows that black holes are not just dead ends. They are cosmic laboratories where our understanding of symmetry and the fundamental laws of physics is stretched to its absolute limit, forcing us to confront the deepest tensions in our description of reality. Just when we thought we had a handle on the universe's grand narrative, a discovery at the very largest scales threw everything we thought we knew into question, revealing yet another profound and mysterious symmetry break. For most of the 20th century, cosmologists operated under a simple, elegant assumption. The expansion of the universe set in motion by the Big Bang must be slowing down. After all, gravity is an attractive force. Every galaxy is pulling on every other galaxy, acting like a cosmic brake on the initial outward rush. The only question seemed to be whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would just keep expanding forever, slowing to a near standstill over trillions of years. This was the expected symmetry, a cosmos governed by the relentless, attractive pull of gravity, leading to a predictable, decelerating future. But in the late 1990s, two independent teams of astronomers were making meticulous observations of distant supernovae to measure this very slowdown. They were using these exploding stars, which have a known intrinsic brightness, as cosmic mile markers to gauge how much the universe had expanded over billions of years. Their results were not just surprising, they were paradigm-shattering. The data revealed that the most distant supernova were significantly fainter than expected. This could only mean one thing: they were much farther away than our models predicted. The expansion of the universe wasn't slowing down at all, it was speeding up. Something was actively pushing galaxies apart, overcoming the collective gravitational pull of all the matter in the cosmos. This discovery of an accelerating universe was so startling and counterintuitive that it earned the teams the Nobel Prize in Physics in 2011. It meant that a fundamental symmetry of our cosmic model was broken. The expected future of a gravitationally dominated, decelerating cosmos was wrong. In its place was a universe being ripped apart by a mysterious, repulsive force we now call dark energy. This force represents a colossal imbalance on the grandest scale imaginable, a dominant pressure that is actively shaping the fate of everything. So what could possibly be causing this repulsive gravity? The leading candidate is something that Einstein himself proposed, then famously discarded as his biggest blunder: the cosmological constant. In his equations of general relativity, Einstein included a term represented by the Greek letter lambda, which represented a constant energy density permeating the vacuum of space itself. This energy has a bizarre property: it doesn't dilute as the universe expands. As new space is created, more of this vacuum energy appears to fill it, maintaining a constant density. And because of the peculiar way general relativity works, this constant energy density exerts a negative pressure, a kind of gravitational repulsion that causes the expansion of space to accelerate. It's as if the empty vacuum itself is endowed with a kind of elastic energy, and the more it's stretched, the more pushback it provides. If this model is correct, then dark energy is simply a fundamental property of space, a cosmological constant woven into the very fabric of reality. But this explanation comes with its own profound puzzle. When physicists try to calculate the expected value of this vacuum energy from quantum field theory, they get a number that is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the entire history of science. This staggering discrepancy suggests we are missing something deep and fundamental about the nature of the vacuum. The alternative to a static cosmological constant is the idea that dark energy is dynamic. Perhaps it's not a constant at all, but a new, exotic field that permeates space, similar to the Higgs field or the inflaton field that drove cosmic inflation. This concept is often called quintessence. A dynamic field could evolve over time, its strength waxing and waning, which would mean the acceleration of the universe might not be a permanent feature. It could change in the future, perhaps even reversing sign and becoming attractive. This idea introduces a new layer of asymmetry, a breaking of the symmetry of a constant vacuum energy in favor of a changing, evolving force. Whether static or dynamic, the presence of dark energy represents a dramatic breaking of the symmetry we expected from a matter-dominated universe. It is now the dominant component of the cosmos, making up about 70% of its total energy content. Its repulsive grip is now the primary director of our cosmic destiny, dictating a future that is increasingly cold, empty, and isolated. As the acceleration continues, galaxies outside our local group will be pushed away from us faster and faster. Their light will eventually be redshifted so far that they will fade from view entirely, vanishing beyond our cosmic horizon. Astronomers in the far future, living in a galaxy like our Milky Way, would look out into a black, empty void. They would see no other galaxies, no evidence of the Big Bang, no clue that a vast, expanding universe ever existed. Their cosmos would appear static and island-like, a profound illusion created by the relentless symmetry-breaking action of dark energy. This force reminds us that the universe is not a static monument but a dynamic, evolving story. The balance we perceive at any given moment is fleeting. The dominance of matter, which allowed for the formation of galaxies and life, was merely a phase, a temporary chapter in a much longer saga, now dominated by this mysterious, repulsive energy. It shows us that symmetry breaking is not just a phenomenon of the distant past. It is an active, ongoing process operating on the very largest scales, continually reshaping the cosmos and reminding us that change is the only true constant. But if the nature of reality is shaped by these seemingly random, historical accidents of symmetry breaking, a deeply unsettling question arises: why these laws? Why these constants, the strength of gravity, the mass of the electron, the exact value of the cosmological constant? These fundamental numbers seem exquisitely, almost miraculously, tuned to allow for a universe that can contain complex structures and, ultimately, life. Tweak any one of them by even a fraction of a percent, and stars would never ignite, atoms would never bond, and the cosmos would be stillborn. This apparent fine-tuning has long been a source of wonder and debate. Is it evidence of a grand designer, or is it simply a staggering cosmic coincidence? Modern physics offers a third, and perhaps even more mind-bending, possibility: that our universe, with its specific set of broken symmetries and physical constants, is not the only one. It may be just one page in an infinite cosmic library known as the multiverse. This idea emerges naturally from two of our most ambitious theoretical frameworks: eternal inflation and string theory. Eternal inflation takes the concept of cosmic inflation and runs with it. We discussed how a scalar field, the inflaton, drove a period of exponential expansion. The theory suggests that this process may never have completely stopped. Instead, inflation could be a perpetual, self-replicating engine. In this picture, the overall multiverse is a vast, ever-expanding foam of spacetime. Most of it is still undergoing rapid inflation, but within this frothing sea, random quantum fluctuations can cause the inflaton field to drop to a lower energy state in localized pockets. When this happens, inflation ends in that specific region, and the released energy creates a hot Big Bang, a new, distinct universe, like a bubble forming in a boiling pot of water. Crucially, the details of this transition, exactly how the symmetry breaks, can vary from bubble to bubble. Each one can freeze in a different configuration of physical laws and fundamental constants. In one bubble universe, the Higgs field might have settled into a different value, giving electrons a much greater mass and preventing chemistry. In another, the strong nuclear force might be too weak to bind protons and neutrons, so no atomic nuclei ever form. Our universe isn't special or fine-tuned. It's simply one of countless bubbles where the random roll of the cosmic dice happened to produce a combination of laws that allows for galaxies, planets, and physicists to ponder their existence. String theory, a candidate for a theory of everything, paints a similar picture but with even more breathtaking scope. It proposes that the fundamental constituents of reality are not point-like particles but unimaginably tiny, vibrating strings. The way these strings vibrate determines the properties of the particles they manifest, as, much like different vibrations of a violin string produce different musical notes. But for the math to work, string theory requires extra spatial dimensions beyond the three we experience, often 6 or 7 of them, curled up into a complex, microscopic shape called a Calabi-Yau manifold. The specific way these dimensions are compactified, their exact geometric shape, dictates the laws of physics that emerge in the macroscopic universe we see. And here's the crucial part. There is not one unique way for these dimensions to curl up. physicists estimate the number of possible stable configurations could be astronomically large, perhaps around 10 to the power of 500. This vast array of possibilities is known as the string theory landscape. Each distinct configuration corresponds to a different vacuum state of the universe, each with its own unique set of physical laws, forces, and particle masses, its own unique pattern of broken symmetries. In this context, our entire cosmos, with all its history and complexity, is just one possible realization, one valley in this incomprehensibly vast landscape of physical realities. This multiverse perspective fundamentally reframes the meaning of symmetry breaking. It suggests that what we once might have considered the one true, perfect set of physical laws is merely the local bylaw of our particular cosmic neighborhood. The grand, overarching symmetry may exist at the level of the entire multiverse, encompassing all possible laws and all possible breakings. Our reality is not the result of a single, definitive break from a perfect state, but rather one momentary configuration in an eternal dance of becoming across a meta-reality of infinite possibilities. This is not just a scientific hypothesis, it's a profound philosophical shift. It challenges our innate tendency to see our universe as central and purposefully designed. Instead, it presents a vision of reality as a vast, perhaps infinite, tapestry of experimentation, where every possible form of existence is realized somewhere. The symmetry breaking that gave us mass, that forged the elements that led to life, is not a unique event but a common occurrence in the metacosmos, playing out in an endless variety of ways. Some universes might flash into existence and vanish almost instantly, too unstable to persist. Others might be vast, empty voids dominated by a crushing cosmological constant. And a precious few, like ours, might strike a fragile, temporary balance that allows for the emergence of complexity and consciousness. This idea invites us to consider that the creative process we've been tracing, the movement from balance to becoming, from symmetry to structure, is not confined to our single universe. It may be the fundamental engine of all existence, operating on a canvas so vast that our entire cosmos is but a single stroke of paint. This cosmic dance between perfect balance and dynamic change isn't just a story told by physicists. It echoes through the deepest currents of human thought, a philosophical tension that has captivated thinkers for millennia. On one side stands the ideal of symmetry, balance, order, and the eternal perfection of abstract forms. On the other is the undeniable reality of becoming, the constant flux, the creative imperfection, and the relentless drive of evolution. This isn't a battle to be won, but a fundamental duality that defines existence itself, a harmony woven from the very tension between these two states. The ancient Greek world offers a stunningly clear view of this divide. In one corner we have Plato, who envisioned a realm of perfect, eternal forms. For him, the physical world we see and touch is merely a shadow, a flawed and imperfect copy of these ideal archetypes. A real circle drawn in sand is always slightly lumpy, but the form of a circle is a concept of perfect, infinite symmetry, untouched by time or decay. Plato's philosophy is a search for this underlying perfection, a belief that true reality is a state of flawless, timeless balance. Then, just a generation earlier, we find Heraclitus, who stood by a river and declared that you can never step into the same water twice. For him, change was not an illusion but the only constant. His famous aphorism, "Everything flows," captures the essence of a universe in perpetual becoming, where stability is a temporary illusion, and the only true reality is the process of transformation itself. These two giants of Western thought frame the debate beautifully. Is reality fundamentally about being or becoming? Is it defined by its perfect, balanced blueprints or by its messy, creative, and constant unfolding? Eastern philosophies, particularly Taoism, have long embraced this duality not as a conflict but as a dynamic, interdependent partnership. The concept of yin and yang is perhaps the most elegant expression of this idea. It isn't a symbol of good versus evil, but of complementary opposites, dark and light, passive and active, receptive and creative, that flow into one another, each containing the seed of the other within itself. A state of perfect, pure yang cannot exist. It would be static and lifeless. It is the constant interplay, the gentle sway between these poles, that generates the energy and creativity of the world. The Taoist sage doesn't seek to eliminate one in favor of the other, but to find harmony within their eternal dance, understanding that the mountain's stability, yin, and the river's flow, yang, are both essential aspects of a single, unified whole. This ancient wisdom finds a powerful echo in our modern scientific story. The universe requires both. Perfect symmetry provides the underlying laws, the stable framework of physics that allows particles to exist and interact predictably. It is the canvas, but symmetry breaking is the paint. It is the dynamic process that uses that stable framework to create everything we see. Without the symmetry of the fundamental laws, there would be no consistency, no mathematics, no physics, just chaos. But without the breaking of that symmetry, there would be no atoms, no stars, no planets, and no life, just a silent, eternal, and featureless equilibrium. The tension between balance and becoming is therefore not a flaw in the system. It is the system. Stability allows for structure to exist, while change allows for that structure to evolve into ever greater complexity. This is the engine of the universe. It is why a snowflake can be perfectly symmetrical in its crystal structure, yet every single one is unique in its detailed pattern. It is why our bodies maintain a stable, symmetrical form overall, yet our internal organs and our brains are wildly asymmetric, optimized for function over perfect form. This duality is the source of all richness and beauty in our experience. A perfectly symmetrical piece of music would be a monotonous drone. It is the departure from the beat, the syncopation, the resolution of dissonance into harmony that creates emotion and meaning. In our own lives, we seek balance in our work, our relationships, our minds, but we also crave growth, learning, and new experiences. We understand that a life in perfect, static balance would be a life not lived. It is the slight imbalances, the challenges that push us out of equilibrium, that force us to adapt, to learn, and to become more than we were. The universe, in its profound wisdom, operates on the same principle. It does not choose between balance and becoming. It uses both. The eternal laws provide the balance, and the spontaneous breaks from that balance fuel an endless becoming. This is the great cosmic creativity, a dance where the partners are stability and change, and the music is the unfolding story of everything. But to truly grasp the profound power of symmetry and its breaking, we must journey beyond the physical world and into the pure, abstract realm of mathematics, for it is here that the concept finds its most precise and powerful language. This isn't about simple shapes, it's about a deep, formal structure that classifies symmetry itself, a field known as group theory. Think of it this way: if you look at a square, you can intuitively see its symmetries. You can rotate it by 90 degrees, 180 degrees, or 270 degrees, and it still looks the same. You can flip it over along its vertical, horizontal, or diagonal axes. Each of these actions is a specific transformation that leaves the square invariant, that is, unchanged in its essential appearance. Group theory is the mathematics that rigorously catalogues all these possible actions for any object, from a simple triangle to the most complex multidimensional crystal. It provides a universal algebra of symmetry, a way to describe not just what is symmetric, but how it is symmetric. This powerful framework didn't emerge from a vacuum. It was born from a revolution in thinking, much of it driven by a brilliant and tragic young mathematician named Évariste Galois in the early 19th century. Galois was obsessed with a problem that had stumped mathematicians for centuries, finding a general formula to solve polynomial equations of degree 5 and higher, so-called quintic equations. While formulas existed for quadratic, cubic, and quartic equations, the quintic resisted all attacks. Galois approached the problem not by trying to find the solutions, but by studying the symmetries between them. He realized that the solutions to any polynomial equation are not isolated numbers. They exist in a relationship with each other, and they can be permuted, swapped around, in ways that preserve certain algebraic truths. He discovered that the key to whether an equation could be solved by a simple formula lay in the structure of the group of these permutations, what we now call the Galois group. If this group had a certain kind of structure, if it was solvable, then the equation could be solved with radicals. For the quintic, he proved this group was too complex, its symmetry too intricate to be broken down in the required step-by-step manner. This was a monumental breakthrough, solving an ancient puzzle by shifting the focus from calculation to structure, from numbers to symmetry. Tragically, Galois died in a duel at the age of 20, his work barely understood at the time. But the seeds he planted grew into the mighty oak of group theory, which now provides the fundamental language for describing symmetry in virtually every branch of modern science. The applications are breathtaking in their scope. In cryptography, the security of the internet relies on the extreme difficulty of reversing certain mathematical operations, a problem rooted in the theory of finite groups. When your browser makes a secure connection to a bank, it's using protocols that leverage the asymmetry between how easy it is to multiply two large prime numbers together, and how astronomically difficult it is to take the result and factor it back into those original primes. This computational asymmetry is a direct application of abstract group theory protecting our digital lives. In chemistry and material science, group theory is indispensable for understanding crystallography. The very definition of a crystal is a material whose atoms are arranged in a repeating, symmetric pattern. Crystallographers use group theory to classify all 230 possible ways atoms can be arranged in three-dimensional space, known as space groups. This classification allows scientists to predict the properties of new materials, from their optical behavior to their electrical conductivity, based solely on their symmetric structure. And of course, as we've seen throughout this journey, modern physics is written in the language of group theory. The standard model of particle physics is essentially a description of the universe based on specific gauge groups, particular kinds of symmetry groups that dictate how particles interact and forces are mediated. The discovery of the Higgs boson was the experimental confirmation that the symmetry of one of these groups, the Electroweak symmetry, is broken in the vacuum of our universe. Mathematics through group theory doesn't just describe static symmetry, it provides a formal toolkit for understanding how and why symmetries break. The process of spontaneous symmetry breaking, which we've seen from the Higgs field to the formation of galaxies, can be mapped perfectly onto mathematical concepts like groups and their subgroups. When a system moves from a high symmetry state to a lower symmetry state, it's mathematically described as moving from a larger symmetry group to one of its smaller subgroups. The possibilities for how this can happen are not infinite. They are strictly constrained and classified by the mathematical structure of the original group. This reveals a stunning truth. The logic of the universe has a deep, inherent preference for certain kinds of patterns. The possible ways for balance to give way to becoming are not random. They are preordained by the abstract relationships of mathematics. This mathematical perspective ultimately enriches our story in a profound way. It shows us that the tension between symmetry and asymmetry is not a vague philosophical concept, but a precise, calculable dynamic woven into the very logic of existence. The universe isn't just breaking symmetry willy-nilly. It is following a hidden geometric script, moving from larger groups to smaller subgroups in a cosmic dance of constraint and possibility. The patterns of a snowflake, the orbits of planets, the fundamental forces between particles, and the very origin of mass itself, all of these are expressions of this deep mathematical reality. The universe, in its heart, is a mathematician, and its most creative work is done through the structured, beautiful, and inevitable breaking of its own perfect symmetries. And this profound understanding of symmetry breaking isn't just a theoretical marvel confined to textbooks and particle accelerators. It's the very bedrock of our modern technological world. We have learned to become masters of imbalance, to harness these cosmic principles and build devices that shape our daily lives. Perhaps the most fundamental example of this is sitting in your pocket or on your desk right now, the transistor. At its heart, a transistor is a tiny, exquisitely engineered device that leverages symmetry breaking to control the flow of electricity. Think of it as an ultra-precise electronic switch. In its natural off state, a certain region within the transistor, called the channel, is symmetric. It has an equal number of positive and negative charge carriers, creating a perfect balance that acts as an insulator, blocking the flow of current. But when we apply a small voltage to a third terminal, called the gate, we deliberately break that symmetry. This voltage creates an electric field that either attracts or repels charge carriers, flooding the channel with one type and depleting the other. This controlled imbalance transforms the channel from an insulator into a conductor, allowing current to flow freely and turning the switch on. This binary flipping between symmetric and asymmetric states, off and on, 0 and 1, is the fundamental language of every computer chip, every smartphone, and every piece of digital technology in existence. Millions, even billions, of these symmetry-breaking events are happening every second inside a processor, performing calculations, rendering images, and connecting us to the world. It is the most widespread practical application of a quantum principle imaginable, and it all hinges on our ability to induce and control a microscopic asymmetry on demand. This theme of controlling light and energy through symmetry breaking finds another spectacular expression in the laser. The word itself is an acronym for light amplification by stimulated emission of radiation, and the process is a masterpiece of forced asymmetry. Inside a laser cavity, you have a collection of atoms, each with electrons sitting in different energy levels. In a normal, balanced state, most electrons are in a lower energy state. This is the equilibrium condition. But to make a laser work, we have to break this natural symmetry. We pump energy into the system, exciting the atoms and forcing a majority of their electrons into a higher, unstable energy state. This creates a population inversion, a highly asymmetric, non-equilibrium condition where there are more excited atoms than relaxed ones. This state is inherently unstable, like a pencil balanced on its tip. All it needs is a single, stray photon to trigger a cascade. When one excited atom spontaneously decays, it emits a photon. That photon then stimulates another excited atom to decay, emitting an identical photon, traveling in the same direction and perfectly in phase. This chain reaction ripples through the entire cavity, with each new photon stimulating the emission of yet more identical photons. What emerges is not ordinary light. which is a chaotic jumble of wavelengths and phases spreading in all directions, a symmetric mess. Instead, a laser produces a coherent, powerful beam of light where every photon is a perfect copy of the others, marching in lockstep. We have taken a system in symmetric equilibrium, broken that symmetry with an energy input, and channeled that imbalance into a beam of incredible purity and power. This technology, born from our understanding of quantum asymmetry, now reads prices at the grocery store, performs delicate eye surgery, streams movies through fiber optic cables, and will likely guide the autonomous vehicles of the future. Perhaps the most visually dramatic technological demonstration of symmetry breaking is superconductivity. In an ordinary piece of metal, electrical resistance arises from a kind of symmetry. Electrons, which carry the current, are individual particles that bounce off the vibrating atoms of the metal's lattice, scattering in random directions and losing energy as heat. It's a chaotic, symmetric dance that impedes the smooth flow of electricity. But when certain materials are cooled to incredibly low temperatures, they undergo a dramatic phase transition. Below a critical temperature, a new collective behavior emerges that breaks the existing symmetry. Electrons, which normally repel each other due to their identical negative charge, suddenly pair up in a coordinated quantum dance. These Cooper pairs act not as individual scattering particles, but as a single, coherent quantum entity. This collective state possesses a new kind of order, a broken symmetry that allows the electron pairs to move through the material lattice without any resistance whatsoever. The electrical current can flow forever in a closed loop without diminishing, a phenomenon with no classical analogy. The most striking demonstration of this is magnetic levitation. When a magnet is brought near a superconductor, the superconductor expels the magnetic field from its interior, an effect called the Meissner effect. But it doesn't just push it away. It does so in a way that can stably lock the magnet in mid-air, hovering over the superconductor as if by magic. This isn't magic, it's the physical manifestation of a broken symmetry, a quantum rigidity that prevents the magnetic field lines from penetrating the material and pins the magnet in a perfect, frictionless balance. This technology is already moving beyond the lab, enabling ultra-powerful magnets for medical MRI machines, maglev trains that float silently above their tracks at hundreds of miles per hour, and may one day form the backbone of lossless power grids that could revolutionize how we distribute energy across the planet. The power of controlled asymmetry extends far beyond the world of physics and into the very chemistry that builds our modern lives, particularly in the field of catalysis. Many molecules, as we've seen, are chiral. They come in left and right-handed versions or enantiomers. For most of the history of chemistry, creating these molecules in the lab resulted in a racemic mixture, a 50-50 blend of both forms. But in pharmaceuticals, this symmetry can be deadly. Often, only one enantiomer of a drug has the desired therapeutic effect, while the other might be inert or, even worse, cause severe side effects. The classic, tragic example is the drug thalidomide, prescribed in the late 1950s to treat morning sickness. One enantiomer provided the intended relief, but the other caused devastating birth defects. This horrific lesson underscored the critical need for asymmetric synthesis, the ability to produce a desired molecule in just one of its chiral forms. Chemists have risen to this challenge by developing chiral catalysts. These are molecules that act as microscopic matchmakers, themselves being asymmetric. When introduced into a chemical reaction, they provide a templated, asymmetric environment that favors the formation of one enantiomer over the other, sometimes with near-perfect selectivity. It's like providing a factory that only makes left-handed gloves. This technology, for which the Nobel Prize was awarded in 2001, is now a cornerstone of modern drug manufacturing, allowing for the production of safer, more effective medications with higher purity and less waste. The same principles are used to create advanced materials with specific properties, like biodegradable plastics and liquid crystals for our displays. In every case, we are not just observing symmetry breaking, we are actively directing it, using our understanding of molecular handedness to impose our own desired asymmetry onto matter, crafting the specific structures we need from the palette of possibilities provided by nature. This conscious application of a cosmic principle, from the quantum structure of a transistor to the chiral center of a life-saving drug, proves that the story of symmetry breaking is not a remote, abstract tale. It is the narrative of our own ingenuity, a testament to our ability to learn the universe's deepest rules and then use them to build a better, more advanced, and more wondrous world. Now, let's bring this cosmic story down to Earth, to the intricate, living systems that surround us every day. If you've ever walked through a forest or snorkeled over a coral reef, you might have been struck by a sense of natural harmony, a perfectly balanced ecosystem. But that perception, much like the perfect symmetry of a snowflake, is a beautiful illusion. Ecology, the study of these systems, reveals a truth that should now feel deeply familiar. Stability and resilience don't come from a state of perfect, static balance, but from a constant, dynamic dance of asymmetry. At the very heart of every ecosystem is a fundamental imbalance, the one-way flow of energy. The sun provides a constant, massive input of energy, but this energy doesn't cycle. It flows through the system in a single direction, from producers to consumers to decomposers, and is eventually lost as heat. This isn't a symmetrical cycle, it's a linear cascade, a river of energy that everything in the ecosystem depends on. Nutrients, by contrast, do cycle, but they are constantly being shifted from place to place, creating local pockets of feast and famine. A leaf falls from a tree, creating a temporary, nutrient-rich patch on the forest floor that decomposers and insects flock to, breaking the symmetry of the soil's composition. This constant, asymmetric movement of energy and materials is the engine that drives all life, preventing any part of the system from settling into a stagnant, permanent equilibrium. This dynamic is perhaps most vividly illustrated in the classic, elegant dance of predator and prey. Picture a population of snowshoe hares in a northern forest, thriving on abundant vegetation. Their numbers grow. This growing abundance of prey creates an opportunity, an asymmetry of resources. The population of lynx, their main predator, soon begins to rise as well, fueled by the plentiful food. But as the lynx hunt more effectively, they begin to reduce the hare population. This creates a new imbalance. With prey now scarce, the lynx population starts to crash from starvation and lower birth rates. And with the predator pressure lifted, the few remaining hares, now with less competition for food, can begin to recover their numbers, starting the entire cycle over again. If you were to graph these populations over time, you wouldn't see two flat, stable lines living in perfect harmony. You would see two oscillating waves, forever chasing each other, forever out of phase. The peak of the lynx population always comes slightly after the peak of the hare population. This is not a failure of the system, it is the system working perfectly. The stability of the predator-prey relationship isn't found in a balanced state, but in the consistent, predictable pattern of their imbalance. It is a stability of process, not of stasis. A perfectly balanced, symmetric state between predator and prey is a fantasy. It would require a world without scarcity, without competition, and without change. The real world is one of constant fluctuation, where temporary asymmetries drive a never-ending story of boom and bust, life and death. that actually maintains the overall health of the ecosystem over the long term. And sometimes the imbalances that renew ecosystems aren't gradual but are sudden, violent, and transformative. Natural disturbances like wildfires, hurricanes, or volcanic eruptions are the ultimate ecological symmetry breakers. A mature, old-growth forest can appear to be a stable, climax community, a state of near-perfect balance. The canopy is dense, shading the forest floor. A few dominant tree species reign supreme, but this stability can mask a hidden fragility and a loss of diversity. Then, a lightning strike ignites a wildfire. The fire is a brutal, asymmetric event that raises the landscape, resetting the clock. It seems like pure destruction, a catastrophe, but in its wake, the fire breaks the monopoly of the mature canopy. It opens up the land to sunlight, clears away thick layers of dead matter, and even releases seeds from certain fire-adapted species like lodgepole pines that require the intense heat to open their cones. The landscape is now a patchwork of different conditions, a mosaic of asymmetries. Sun-loving pioneer species which couldn't compete in the shade rush in to colonize the open spaces. This initial burst of diversity is often far greater than what existed in the mature forest. Over time, through a process called succession, these species modify the environment, making it suitable for other species to move in, slowly building back towards a complex forest. But it will never be the same as it was. The disturbance ensures a new, unique path of becoming. We see this same pattern on coral reefs. A powerful hurricane can smash large sections of a reef into rubble. While devastating for the existing coral, this destruction creates new, bare substrate on the seafloor, a blank canvas for new life. Coral larvae, floating in the currents, can settle on this fresh rock and begin to grow, often leading to a more diverse and resilient reef community than the one that was there before. These disturbances prevent any single species from achieving total, permanent dominance. They are the ecosystem's way of shaking the etch-a-sketch, of breaking the symmetry of an established order to make room for innovation, adaptation, and renewed vitality. Resilience, therefore, isn't the ability to resist change, but the capacity to recover from it, and that recovery is always fueled by the creative potential of asymmetry. This ecological perspective brings our cosmic journey full circle. From the quantum fluctuations frozen into the cosmos by inflation to the hurricane that clears a path for new life on a reef, the same fundamental principle is at work. A state of perfect symmetry, whether it's a uniform universe, a 50-50 mixture of molecules, or a stable, monolithic forest, represents a kind of potential energy. It is a poised, pregnant state, full of possibility but devoid of interest, structure, or life. It is the breaking of that symmetry, the choice of a specific path, the introduction of a fluctuation, the impact of a disturbance, that releases that potential energy and allows for the emergence of complexity, diversity, and evolution. Stability in nature is never the stillness of a pond without a ripple. It is the dynamic, resilient stability of a river that maintains its course even as every drop of water within it is constantly moving, changing, and being replaced. The ecosystems we depend on for clean air, fresh water, and fertile soil are not delicate china shops that will shatter if touched. They are complex, adaptive systems that have evolved to incorporate imbalance and disruption into their very fabric. They teach us that seeking to freeze nature in a state of perfect, unchanging balance is to misunderstand how life actually works. True sustainability isn't about preventing change. It's about understanding the rhythms of asymmetry and working with them, allowing for the natural processes of disturbance and recovery that have sustained life on this planet for billions of years. In the end, a walk in the woods is not a walk through a balanced, symmetrical world. It is a walk through a living testament to the same creative, cosmic tension that filled the universe with galaxies. A world forever becoming, forever enriched by its own beautiful, necessary imperfections. This dance of asymmetry is not confined to the natural world or the cosmos. It is the very rhythm of human civilization itself. We often speak of equality as a noble ideal, a state of perfect balance where resources, opportunities, and power are distributed evenly. But history shows us that this state of perfect social and economic symmetry is, like the featureless early universe, a theoretical possibility that is inherently unstable and ultimately sterile. The societies that have thrived, the cultures that have flourished, and the eras that have catapulted humanity forward are not stories of perfect equilibrium, but of dynamic and often disruptive imbalance. Consider the breathtaking explosion of creativity we call the Renaissance. For centuries prior, much of European society was structured under a relatively rigid, symmetric feudal system, a pyramid with a monarch and papacy at the apex and serfs at the base, a hierarchy that aimed for a static, God-ordained order. But this symmetry began to crack. The Black Death, a horrific asymmetry of mortality, devastated the population, which ironically broke the feudal system's grip by creating a labor shortage that empowered common workers. The fall of Constantinople sent scholars fleeing west with ancient texts, creating an asymmetry of knowledge concentrated in Italian city-states. And crucially, the rise of wealthy, competing merchant families like the Medici in Florence created a massive asymmetry of wealth and patronage outside the traditional aristocracy and church. They didn't just hoard their money, they invested it in artists, architects, and thinkers not for immediate utility, but for the glory it would bring their city and their name. This concentration of capital and competition between patrons broke the cultural monopoly of the church and created the fertile, imbalanced ground where a Michelangelo or a Leonardo da Vinci could be funded to experiment, innovate, and create masterpieces that would redefine what it meant to be human. This wasn't a story of equal distribution. It was a story of concentrated resources fueling an unparalleled outburst of human potential. The same pattern repeats with the Industrial Revolution. It wasn't born from a society of perfect economic balance. It was ignited in Britain due to a specific asymmetric cocktail of factors. A concentration of capital from global trade and colonial enterprises, geographic advantages like abundant coal and iron deposits, a legal framework that protected patents and private property, and a series of agricultural innovations that freed up a large workforce. This created immense inequalities. The grim, soot-choked factories and the vast wealth of the new industrial barons stood in stark contrast. The human cost was enormous and sparked necessary social movements and reforms. But it also undeniably drove staggering technological progress. The fierce competition between inventors and industrialists, all vying for a piece of a new market, accelerated innovation at a breathtaking pace. The steam engine, the spinning jenny, the power loom, these weren't created in a vacuum of comfortable equality. They were the products of a pressurized, competitive, and highly asymmetric environment. This is the double-edged sword of social and economic asymmetry. On one edge, excessive, entrenched imbalance, the kind that creates vast, unbridgeable gulfs between a privileged few and an impoverished many, is a recipe for instability, resentment, and conflict. It corrodes social trust, stifles mobility, and can lead to revolution or collapse. This is the destructive potential of a symmetry break that has gone too far, where the system cannot find a new, functional equilibrium. But the other edge is the engine of progress. Moderate, fluid asymmetries in wealth, power, and influence act like a pressure differential in the atmosphere. They create the winds of change. They foster competition not just in business but in ideas. They provide the capital for ambitious projects that benefit society as a whole, from funding basic scientific research to building infrastructure. They create incentives for innovation, for taking risks, for developing new skills. A society that achieves a forced, absolute equality would likely be a society without great art, without transformative technology, and without the dynamic cultural exchange that comes from different groups having different resources, perspectives, and specialties. Our global cultural diversity itself is a form of asymmetry, a beautiful patchwork of different languages, traditions, and worldviews that have arisen from our groups developing in relative isolation from one another. When these asymmetric cultures then meet and interact, whether through trade, migration, or even conflict, the friction generates incredible creativity, new ideas, and social evolution. This human experience mirrors the fundamental cosmic principle we've traced from the Higgs field to the evolutionary niche. Becoming requires a departure from equilibrium. Stasis is the enemy of progress. Just as the universe needed to break its perfect symmetry to create galaxies and life, human societies seem to need a certain degree of productive tension, of competitive imbalance, to drive innovation, art, and advancement. The eternal challenge, of course, is to manage these asymmetries, to build systems that allow for the productive, creative friction of competition and inequality, without letting it curdle into the destructive, oppressive friction of injustice and immobility. It is in navigating this tension, in finding the dynamic sweet spot between stagnation and chaos, that we write the ongoing story of our civilization. This drive toward asymmetry isn't just a feature of our brains or our societies. It operates at the very core of our individual psychology, shaping how we think, learn, and ultimately who we become. Our minds, much like the universe itself, seem to have a deep-seated preference for order and consistency. We build mental models of how the world works, symmetrical frameworks of belief that allow us to predict outcomes and navigate our lives with a sense of stability and coherence. But this internal equilibrium is constantly being challenged by new information and experiences that don't quite fit, creating a powerful psychological tension that forces us to grow. This process is perfectly captured by the concept of cognitive dissonance, a term coined by psychologist Leon Festinger. Cognitive dissonance is the mental discomfort or stress we feel when we hold two or more conflicting beliefs, ideas, or values at the same time, or when our behavior contradicts our deeply held beliefs. It's a state of profound psychological asymmetry, a crack in our mental symmetry that demands resolution. Imagine a person who firmly believes themselves to be an ethical, honest individual, but then finds themselves telling a significant lie to get out of a social obligation. These two ideas, I am honest and I just lied, cannot comfortably coexist. The symmetrical self-image has been broken. The resulting dissonance is a powerful motivator for change. The individual might resolve this tension by changing their behavior, confessing the lie, by changing their cognition, deciding the lie wasn't really that bad or was necessary, or by adding a new justifying thought. Everyone does it sometimes. This internal negotiation is a classic example of symmetry breaking on a personal level. The mind cannot tolerate the unstable state of contradiction. It must reorganize itself into a new, more complex, and once again coherent, though now altered whole. This journey from mental symmetry through dissonance to a new understanding is the very engine of learning, a process beautifully mapped out by the pioneering psychologist Jean Piaget. He described cognitive development not as a smooth, linear accumulation of facts, but as a series of revolutionary shifts. Children, he observed, operate with mental frameworks he called schemas. A toddler might have a simple schema for dog, a four-legged furry animal. This schema works well until the child encounters a cat, which also has four legs and fur. The new information fits comfortably into the existing schema. Piaget called this assimilation. It maintains the mental symmetry, but then the child sees a horse for the first time. It's much larger, has a different sound, and perhaps a saddle. This new information doesn't fit the existing dog schema at all. This creates a state of imbalance, a cognitive dissonance that Piaget termed disequilibrium. To resolve this discomfort, the child must accommodate. They must break the old schema and create a new, more sophisticated one. They develop a new category for horse and perhaps a broader super-category for animals. The old, simple symmetry is gone, replaced by a more nuanced and accurate mental model of the world. This cycle of equilibrium, disequilibrium, and re-equilibration is how we build intelligence throughout our lives. It's a process that requires us to willingly tolerate the discomfort of not knowing, of having our symmetrical certainties shattered, in order to reach a higher level of understanding. Without this willingness to embrace psychological asymmetry, our learning would simply stop. We would become mentally rigid, forcing every new experience to fit into our existing and increasingly inadequate boxes. This theme of breaking internal symmetry to achieve a more complete self finds its most profound expression in the work of Carl Jung and his concept of individuation. Jung saw the human psyche as beginning in a state of unconscious unity, a kind of primal symmetry where all potential is contained but undeveloped. The journey of life, the goal of individuation, is to become a fully realized, unique individual by consciously integrating all the disparate and often conflicting parts of our personality. This requires a massive and ongoing act of internal symmetry breaking. We must confront our persona, the symmetrical mask we show the world, and acknowledge the shadow, the hidden, often rejected parts of ourselves that don't fit that perfect image. This is a deeply uncomfortable process. It means admitting that we are not just the good, kind, and patient person we present to others, but that we also harbor jealousy, anger, and selfishness. Integrating the shadow doesn't mean acting on these impulses. It means acknowledging their existence, robbing them of their autonomous power, and thereby becoming a more whole and authentic person. This is followed by engaging with the anima in men or animus in women, the contra-sexual archetype that represents the other half of our psychological makeup. A man must recognize and integrate his feminine aspects like intuition and empathy to move beyond a one-sided, hyper-masculine persona. A woman must integrate her masculine aspects like logic and assertiveness. This process continually shatters our simplistic, symmetrical self-concepts, forcing us to hold opposing traits in tension, to be both strong and vulnerable, both logical and intuitive, both disciplined and spontaneous. The result of this lifelong journey is not a new, perfectly symmetrical self, but a complex, dynamic, and resilient individual who can embrace their own contradictions. The end point, which Jung called the self with a capital S, is a new kind of psychological center, but it's a center that has been forged through the constant breaking and reforming of our inner symmetries. It is the ultimate personal expression of the cosmic truth that wholeness is not found in perfection, but in the embrace of our entire, beautifully imperfect being. This inner work is not just about personal comfort. It is the bedrock of adaptability and innovation in an ever-changing world. Mental rigidity and over-attachment to our existing symmetrical beliefs is a major hindrance to survival and success. Think of a company that clings to a once successful business model long after the market has shifted, or an individual who refuses to learn new technologies because it disrupts their familiar way of doing things. This inflexibility is a form of psychological entropy, a slow descent into irrelevance. In contrast, a mind that is open to asymmetry, that can tolerate the discomfort of dissonance and uncertainty, becomes resilient and innovative. Such a person can pivot when circumstances change, can hear challenging feedback without becoming defensive, and can synthesize opposing ideas to create something entirely new. This psychological flexibility is what allows scientists to abandon a favored hypothesis when the data contradicts it. It allows artists to break with tradition and forge new movements, and it allows all of us to learn from our mistakes and grow from our failures. The tension we feel when our beliefs are challenged is not a sign that something is wrong. It is a sign that we are being presented with an opportunity to evolve. By leaning into that asymmetry instead of fleeing from it, we participate in the same creative process that shaped the cosmos. We break our own internal symmetries not to create chaos, but to make room for a more complex, more adaptive, and more authentic version of ourselves, proving that the universe's most fundamental law, that becoming requires a break from balance, is written into the very fabric of our minds. Now let's turn our ears to the cosmos of human creativity, to the world of music and sound, where the principles of symmetry and its breaking are not just abstract concepts, but the very tools used to stir our deepest emotions. Music is a universe built on patterns, and at its foundation lies a deep, intuitive love for symmetry. A simple, steady 4/4 time signature gives us a reliable pulse, a symmetrical framework we can tap our feet to. A major chord built on perfectly stacked thirds feels resolved and harmonious, a vertical symmetry of sound that provides a sense of home and stability. These symmetrical structures are the canvas, the predictable order that makes the music intelligible and comforting to our brains, which are hardwired to seek out patterns. But if music were only symmetry, it would be as monotonous as a metronome, technically perfect but emotionally barren. The magic, the true artistry, happens in the deliberate and calculated breaking of that symmetry. This is where composers and musicians become masters of controlled imbalance, manipulating our expectations to create drama, emotion, and movement. The most immediate way they do this is through rhythm, specifically with a device called syncopation. Syncopation is the musical equivalent of a surprise party. It's the deliberate disruption of the expected rhythmic flow, placing emphasis on the offbeat, on the weak part of the measure where we don't expect it. Instead of the strong, predictable 1, 2, 3, 4, you get a pattern that makes you want to move, that creates a sense of playful tension. You can hear this everywhere, from the complex polyrhythms of a West African drum circle to the infectious backbeat of a rock and roll song where the snare drum cracks on the 2 and the 4, pushing against the grain of the beat. This rhythmic asymmetry is the engine of dance music. It's what makes your body want to respond before your brain even understands what's happening. This same principle of tension and release operates on the level of harmony with the powerful tool of dissonance. Dissonance is a harmonic asymmetry, a clashing of notes that creates a sense of instability, unease, or longing. Imagine a composer leading you through a beautiful, symmetrical chord progression, everything feeling settled and right. Then they introduce a chord that is slightly off, a combination of frequencies that vibrate against each other in a way that feels unsettled and restless. This is dissonance. It creates a powerful psychological need for resolution, a yearning to return to the consonant, symmetrical chord that feels like home. The entire emotional arc of much Western classical music is built on this journey from consonance to dissonance and back again. The bittersweet ache of a piece by Chopin or the thrilling suspense in a film score by John Williams is often just the masterful application and prolonged teasing of dissonance, stretching the asymmetry to its breaking point before finally granting the audience the cathartic release of resolution. We can trace this beautiful dialogue between balance and imbalance through different genres. In a Bach fugue, the mathematical symmetry of the counterpoint is absolute. The melodies are intricate mirror images of each other. Yet within that rigid structure, Bach weaves moments of harmonic tension that make the piece feel alive and yearning, not just like a mechanical exercise. Jump ahead to the world of jazz, and asymmetry becomes the entire philosophy. Jazz is the art of spontaneous symmetry breaking. Musicians take a symmetrical song structure, the chord changes of a standard like Autumn Leaves, and use it as a launching pad for improvisation. They play with the rhythm, syncopating and swinging the notes. They layer dissonant chords and altered scales over the harmony, creating moments of breathtaking tension that they then resolve in unexpected ways. A jazz solo is a real-time experiment in controlled chaos, a celebration of how individuality and imperfection can create something far more beautiful than perfect adherence to the chart. Even in modern pop production, these principles are at work. A producer might build a track on a perfectly looped, symmetrical drum machine pattern. Then, to make it breathe and feel human, they'll introduce a slight swing or shuffle quantize, a barely perceptible asymmetrical push and pull to the timing. They might add a synth pad with a slightly detuned oscillator, creating a rich, shimmering chorus effect that is inherently slightly out of phase and asymmetrical. These intentional imperfections are what give the music its warmth, its character, its soul. It turns out our ears, much like our eyes gazing at the Parthenon, are not actually drawn to perfect, sterile symmetry. We are captivated by the interplay between the expected and the unexpected. The symmetrical structure provides the foundation we can trust, while the asymmetrical elements, the syncopated rhythm, the dissonant chord, the improvised flourish, provide the story, the emotion, and the humanity. Music teaches us that beauty is not a state of perfect balance, but a dynamic relationship between balance and deviation. It is a direct echo of the cosmic theme we've followed from the beginning, proving that the most compelling structures, whether a universe, a life, or a simple melody, are those that find their vitality in the creative and beautiful tension between order and chaos. But if our journey so far has taught us anything, it's that the universe's creativity often lies hidden in the spaces between perfect order and pure randomness. To find it, we need to look at systems that are exquisitely sensitive, where the tiniest of nudges can cascade into monumental consequences, and where patterns repeat not with rigid perfection, but with a kind of organized irregularity. This brings us to two of the most fascinating ideas in modern mathematics, chaos theory and fractal geometry, which together reveal a breathtaking new layer to our story of symmetry and its breaking. Let's start with chaos, a word that conjures images of utter randomness and unpredictability. But in mathematics, chaos has a very specific and strangely beautiful meaning. We're talking about deterministic chaos. This is a crucial distinction. A deterministic system is one that is not random at all. Its future is completely determined by its initial conditions, following a strict set of rules. There's no dice rolling, no coin flipping involved. In theory, if you know the starting state perfectly, you should be able to predict its future perfectly forever. This is the promise of a perfectly symmetric predictability. But in chaotic systems, this promise is broken in the most dramatic way possible. These systems exhibit what's poetically known as the butterfly effect, the idea that the delicate air currents from a butterfly flapping its wings in Brazil could, through a long and complex chain of atmospheric cause and effect, set off a tornado in Texas weeks later. The technical term is sensitive dependence on initial conditions. It means that two starting states that are almost identical, differing by an amount so small it's practically immeasurable, will diverge from each other exponentially over time, leading to wildly different outcomes. This breaks what we might call predictive symmetry. The laws governing the system are perfectly deterministic and symmetric in time, but our ability to actually use those laws to make long-term predictions is shattered. We can know the rules perfectly, but we can never know the starting conditions with infinite precision. That tiny, imperceptible uncertainty is amplified by the system's own internal dynamics until any semblance of predictable order vanishes into what looks like randomness. It's symmetry breaking on a monumental scale where the inherent limitations of measurement meet the explosive mathematics of nonlinearity. A classic and wonderfully simple example of this is the double pendulum. Take a standard pendulum which swings back and forth with a regular, predictable, and symmetrical rhythm. Now attach a second pendulum to the end of the first one. The equations that govern this double pendulum are still perfectly deterministic. There is no randomness in the math, but the behavior of this system is breathtakingly chaotic. Give the double pendulum a gentle push from a starting position that is almost, but not quite, identical to a previous push, and within just a few swings, its motion will become completely uncorrelated with its previous path. It will flip, whirl, and spin in a wildly unpredictable dance, even though it is obeying Isaac Newton's laws with absolute fidelity. The predictive symmetry is broken not by the laws, but by the system's exquisite sensitivity. This is the essence of deterministic chaos. Order begets chaos, and deep within that chaos, as we'll see, lies a new kind of order. This leads us directly to the stunning world of fractals. While chaos theory shows us how symmetry breaks in time, fractal geometry shows us how a broken symmetry can create a new, deeply complex form of order in space. The term fractal was coined by the mathematician Benoit Mandelbrot, and it describes shapes that are self-similar across different scales. What does that mean? It means that if you zoom in on a small part of the object, it looks similar, though not necessarily identical, to the whole thing. It's a pattern that repeats not with perfect symmetry, but with variations, a kind of textured, recursive asymmetry. Think of a coastline. If you look at it from a satellite, it has a certain level of roughness with bays, peninsulas, and inlets. If you then land on a beach and look at a single rock formation at the water's edge, you'll see the same kind of roughness on a smaller scale, tiny bays, miniature peninsulas, and small inlets in the rock itself. Zoom in further with a microscope to look at the surface of a single grain of sand from that beach, and you'll likely see the same pattern of roughness etched into its surface. The coastline isn't perfectly self-similar. A tiny bay in a rock isn't a perfect miniature copy of the great bay you saw from space. But the pattern, the statistical texture of irregularity, repeats itself across a vast range of scales. This is a broken symmetry. It's not the perfect translational or rotational symmetry of a crystal lattice. It's a more organic, statistical symmetry where the degree of complexity remains constant, even as the scale changes. The most famous fractal is arguably the Mandelbrot set, a mathematical object of infinite complexity generated by an astoundingly simple formula: z goes to z squared plus c. When you plot this simple rule on the complex plane, it doesn't create a simple circle or a square. It creates a boundary of infinite intricacy. As you zoom into the edge of the Mandelbrot set, you find an endless parade of shapes, miniature versions of the main set, swirling spirals, seahorse valleys, and an infinite variety of patterns that are never exactly the same, but are always variations on a theme. It is a perfect visual metaphor for how a simple, symmetric rule can give birth to a universe of infinite, asymmetric complexity. It's a mathematical demonstration that you don't need complex ingredients to create complex results. You just need a simple, nonlinear rule and the power of iteration and feedback. So how do chaos and fractals come together? They are two sides of the same coin, both arising from nonlinear, iterative systems. A chaotic system, like the weather, has a fractal structure. If you look at the graph of how a chaotic variable changes over time, its pattern has a self-similar quality. A small, turbulent patch of air behaves in a way that is statistically similar to a large weather system. This is why weather prediction is so difficult beyond a week or so. The atmosphere is a chaotic system whose dynamics create fractal patterns, breaking the symmetry of long-term prediction while simultaneously creating a hidden statistical order within the apparent disorder. This mathematics of complexity shows us that symmetry breaking isn't just a one-time event, like the Higgs field settling into its value. It is an ongoing, dynamic process inherent in nearly all nonlinear systems around us. It's present in the branching of our lungs and circulatory systems, which maximize surface area for absorption in a limited volume through fractal branching. It's in the forked lightning bolt seeking the path of least resistance, and in the stock market's unpredictable crashes and rallies that somehow follow a fractal pattern in their volatility. These systems are not random. They are following rules, but the interaction of those rules creates feedback loops that amplify tiny differences and break symmetries, leading to the emergent patterns of complexity that define our world. It deepens our understanding of becoming immeasurably. We don't need a divine hand or a random accident to create the rich complexity of a forest or a galaxy. We just need simple rules repeated over and over, interacting with themselves in a feedback loop that inevitably breaks symmetries and gives rise to the beautiful, structured, and unpredictable world we call home. And so our journey through the cosmos of broken symmetry brings us to the very edge of human knowledge, to the laboratories and observatories where the next great revelations are being pursued. This is not the end of the story, but a new chapter being written in real time, as scientists around the world push the boundaries of technology and theory to probe the deepest mysteries of imbalance. The questions that drive this research are as profound as they are fundamental. What other symmetries remain to be broken, and what new physics lies hidden in those cracks? At the forefront of this exploration is the Large Hadron Collider, the most powerful particle accelerator ever built. Having already confirmed the existence of the Higgs boson, the LHC is now hunting for phenomena that lie beyond our current standard model. Physicists are meticulously analyzing the decay patterns of the Higgs itself, searching for tiny deviations from the predicted outcomes. Any slight anomaly could be the first hint of a new particle or force, a sign of a deeper symmetry that was broken in the early universe and has remained hidden until now. They are also searching for evidence of supersymmetry, an elegant theoretical framework that proposes every known particle has a heavier, superpartner particle. This theory would restore a beautiful symmetry between matter particles and force carriers, and it could provide a compelling candidate for the dark matter that shapes our galaxies. Finding even a single superpartner would represent one of the most significant symmetry breaks in our understanding since the Higgs, opening a portal to a whole new layer of reality. But the search extends far beyond the underground tunnels of CERN. Astronomers are turning our most powerful telescopes into time machines, peering back across billions of years to witness the universe's first moments. Projects like the Simons Observatory and the Future Lightbird satellite are mapping the cosmic microwave background, the afterglow of the Big Bang, with unimaginable precision. They are hunting for the faintest imprint of primordial gravitational waves, ripples in spacetime itself that were generated during the violent period of cosmic inflation. Detecting this specific pattern would be the ultimate smoking gun, providing direct evidence for that grandest of all symmetry breaks and telling us about the energy scales at which inflation occurred, potentially tying it to new physics at the quantum gravity scale. Meanwhile, the mystery of dark energy is being investigated by massive sky surveys like the Dark Energy Spectroscopic Instrument (DAISY) and the upcoming Euclid Space Telescope. By measuring the precise distances to millions of galaxies and tracking how the expansion rate of the universe has changed over cosmic history, these projects aim to determine whether dark energy is truly a constant cosmological constant or a dynamic force field that has evolved over time. The answer will tell us if the current accelerating expansion is a permanent feature of the cosmos or just another phase in a long series of cosmic transformations, another shift in the balance of fundamental symmetries. And then there is the most profound theoretical frontier of all, the quest to unify quantum mechanics with general relativity into a single theory of quantum gravity. At the incredibly tiny Planck scale, a distance of 10 to the minus 35 meters, the smooth, continuous symmetry of spacetime itself is predicted to break down. It is thought that spacetime might become granular or foamy, losing its classic structure altogether. Theories like string theory and loop quantum gravity are attempts to describe this realm where the very concepts of here and there may cease to have meaning, suggesting that the spacetime we experience is itself the result of a symmetry that broke as the universe cooled from the Big Bang. Uncovering this would revolutionize our understanding of reality, showing that even the stage upon which the cosmic drama plays out is a product of becoming. The implications of this research stretch into seemingly unrelated domains, even touching the mystery of consciousness. The process of quantum state reduction, the collapse of the wave function, is a fundamental symmetry break that creates definite reality from a cloud of possibilities. Some interpretations of quantum mechanics, like the Orch-or theory, propose that this collapse is not random but is influenced by processes within the brain, suggesting a deep connection between the physics of symmetry breaking and the emergence of subjective experience. While highly speculative, it highlights a breathtaking possibility that the same fundamental principle that gave mass to particles and form to galaxies might also be intimately involved in the arising of awareness itself. This is the thrilling and humbling frontier of modern physics. We are no longer just cataloging the constituents of the universe, we are excavating the very processes that brought it into being. Every new experiment, every deeper observation, is an attempt to read the cosmic recipe, to understand how the pristine symmetry of the initial state was sequentially broken to produce the rich, complex, and beautiful reality we inhabit today. The drive to understand symmetry breaking is more than a technical pursuit. It is a fundamental human yearning to understand our own origins, to trace the line of causality from the first moment of imbalance all the way to the fact that we are here now, able to ponder it all. It is a quest that promises to reveal not just new particles or forces, but a deeper truth about the creative engine of existence itself. Yet this incredible power to break symmetries and shape our world comes with a profound and sobering responsibility. For the first time in the 4-billion-year history of life on Earth, a single species has gained the ability to consciously direct the process of symmetry breaking, to become an active agent in the cosmic dance between balance and becoming. This is not a role we can take lightly. With every technological leap, every intervention in nature's delicate equilibria, we are faced with a critical ethical question. Just because we can break a symmetry, should we? And if we do, how do we ensure that the new world we create is not just more advanced but truly better? Consider the revolutionary field of genetic engineering, particularly CRISPR technology. This tool allows us to act as editors of the very code of life, to break the symmetric process of natural inheritance that has governed evolution for eons. We can now snip out genes that cause devastating hereditary diseases, offering the hope of eradicating human suffering on a generational scale. This is a breathtakingly positive application, a deliberate and compassionate breaking of a cruel genetic symmetry that has caused immense pain. But the same technology can be used to shatter other symmetries with far more ambiguous consequences. What about editing genes for enhanced intelligence, physical strength, or aesthetic traits? This could open a door to a new kind of asymmetry, a societal split between a genetically enhanced class and a natural-born one, potentially creating inequalities more profound and permanent than any we have known. The symmetric chance of the genetic lottery, for all its randomness, has historically been a great equalizer. Deliberately breaking that symmetry requires immense wisdom to ensure we don't cure one ill only to create a far greater one, trading biological suffering for a fractured humanity. The ethical imperative here is to wield this power not for mere optimization, but for healing, and to do so within a framework of justice and universal access. Our capacity for large-scale environmental manipulation presents another monumental ethical challenge rooted in symmetry breaking. For millennia, the Earth's climate system has maintained a dynamic equilibrium, a complex symmetry of energy input and output that has allowed life to thrive. Human industry has already drastically broken that balance, releasing greenhouse gases that trap heat and push the system toward a new, warmer state. Now, we are developing technologies to break the symmetry yet again in an attempt to counter our own mistake, a field known as geoengineering. One proposed method, solar radiation management, involves injecting reflective particles into the upper atmosphere to bounce a small percentage of sunlight back into space, effectively mimicking the cooling effect of a large volcanic eruption. On paper, it could be a rapid way to lower global temperatures, but this would be a global, deliberate breaking of the planet's energy balance with unknowable side effects. It could alter rainfall patterns, potentially causing droughts in some of the world's most vulnerable agricultural regions and flooding in others. It would do nothing to address the root cause of ocean acidification from absorbed carbon dioxide. And it creates a terrifying dependency. If we started such a program and then stopped, temperatures could skyrocket at a catastrophic rate. The ethical dilemma is stark. Do we risk the unpredictable consequences of a massive, intentional planetary intervention to mitigate a known but gradual threat? Or does the sheer scale and irreversibility of such an act demand that we focus solely on reducing emissions at their source, a harder but far less risky path? This isn't just a technical question. It's a philosophical one about our right to deliberately break planetary symmetries and our obligation to the generations who will inherit the consequences of our choices. This need for ethical guidance extends to the digital realm as well. The algorithms that curate our news feeds and social media experiences are designed to break the symmetry of information exposure. They learn our preferences and biases, then feed us more of what we are likely to engage with, creating a personalized but deeply asymmetric information landscape. This has broken the shared, common ground of a public square, fueling political polarization and the spread of misinformation. The engineers who design these systems are making ethical choices, whether they realize it or not, about which symmetries to break and for what purpose, often prioritizing engagement over truth and profit over social cohesion. The cosmic principle we've followed throughout this journey teaches us that symmetry breaking is neither inherently good nor evil. It is simply a powerful mechanism of change. Fire can cook a meal or burn down a forest. A chisel can sculpt a masterpiece or deface a monument. Our task, as conscious beings who now hold these tools, is to align our interventions with a deep sense of responsibility and a long-term vision for a flourishing world. We must strive for a harmony between balance and becoming, not by refusing to change, but by guiding that change with wisdom, foresight, and an unwavering commitment to the common good. This means building robust regulatory frameworks for new technologies long before they become widespread. It means prioritizing precaution and inclusive dialogue when dealing with global systems we don't fully understand. It means asking not only can we do it, but why should we do it, who will benefit, and who might be harmed. The story of the universe shows us that imbalance is the source of all creation, but it is a force that must be channeled with care. Our greatest achievement will not be our power to break symmetries, but our wisdom to do so in a way that creates a world that is more just, more beautiful, and more alive for all. So here we stand at the end of our journey, having traced a single, powerful thread from the quantum vacuum to the conscious mind. We began with a snowflake, a symbol of perfect balance, only to discover that its beauty is a surface illusion masking a deeper truth. At every scale, across every discipline, we have found the same story repeating itself. The universe does not crave perfect symmetry. It thrives on breaking it. This tension between balance and becoming is not a design flaw or a cosmic accident. It is the fundamental creative engine of reality itself. It is the reason our universe is a vibrant, evolving tapestry of galaxies, stars, planets, and life, rather than a silent, static, and featureless void. From the first crack in the electroweak force that granted particles mass, to the quantum fluctuations inflated to cosmic proportions that seeded the galaxies, to the molecular handedness that made life possible, and the neural asymmetries that grant us consciousness, every step forward in the story of everything has been a step away from perfect equilibrium and toward magnificent, complex imperfection. This is the profound symphony that physicist Frank Wilczek so eloquently described. The universe is not a single, sustained note of perfect harmony. It is a rich, dynamic, and evolving composition built on the interplay between the elegant structure of symmetry and the creative, liberating power of its breaking. The laws of physics provide the fundamental score, the beautiful, invariant rules that make the cosmos predictable and lawful. But the music, the breathtaking diversity and drama of existence, comes from the moments where that score is interpreted, where the instruments improvise, and where the performance breaks free from rigid repetition to create something new, unexpected, and alive. We are not merely the audience for this symphony, we are a part of its melody. The very atoms in our bodies, forged in the hearts of long-dead stars, are stardust created by broken nuclear symmetry. The thoughts you're having right now are the product of a brain whose power comes from its functional asymmetries. Your ability to appreciate art, music, and the beauty of a sunset is rooted in this cosmic principle. You are in every way a creation of calculated imbalance, and that invites us to see our own lives and our world through a new lens. The pursuit of perfect balance, of a life without tension or challenge, is a pursuit of stillness that is ultimately at odds with the fundamental nature of the cosmos. It is in the imbalances, the challenges that push us to adapt, the new ideas that disrupt our thinking, the unexpected events that force us to grow, that we find the source of our own creativity, resilience, and humanity. The beauty is not in spite of the imperfection, but because of it. So the next time you see the asymmetrical pattern of branches against the sky, or hear the syncopated rhythm in your favorite song, or even feel the internal tension of a challenging idea, remember that you are witnessing the same cosmic force that shaped the universe. You are hearing a faint echo of the great symphony of symmetry and its breaking. We would love to hear your thoughts on this. Where do you see this tension between balance and becoming in your own world? Share your reflections in the comments below. And if you've enjoyed this deep dive into one of nature's most beautiful secrets, be sure to subscribe and hit the bell so you don't miss our next exploration into the mysteries of